Hello, good morning, sir. Can you hear me?
Hi, good morning. Yes, Pushpraz, I can hear you. What about
Oh,
you? Can you hear me? A lot of echo looks like.
no. It's very clear.
It's very
No
clear.
problem.
Okay,
Yes.
so it's on my side. I can see the echo.
Oh, but I think everybody is muted here actually. So only I am speaking. So I don't know if I switch off my mic. Then
Okay,
so I am
try.
switching off my mic. You please tell me
Yeah,
whether you are still listening the
okay,
echo.
okay. Let me try. And now I don't see any echo. Whatever I'm talking, very clean. Okay,
Okay, so
fine.
maybe it is my mic.
It
Maybe.
was your mic giving the echo actually.
Yes, but anyways, I will switch off my mic while you talk.
Okay, that's wonderful. So everything going well?
Everything is going very well. So basically, this link is only for this. So this is the direct link. That's why we are able to see some people inside.
Uh-huh.
And there is another link which is running for the conference, and it is a YouTube link also. So some people will be listening on the direct
YouTube.
on another link.
Oh,
So
that
yeah,
interesting.
so that is fine. So I think there is a talk going on until 11 o'clock. This is a plenary talk.
Right.
So let's just wait for this to get over, and then
Yeah,
we start our session.
sure.
Okay.
Okay.
You please share your slides also. So
I can.
let's see
Okay,
if
let
there is
me.
no problem.
Let me share. Let me share. Yep. Okay.
Oh yeah,
It's
yeah.
okay.
It is good. It is good.
It's good.
Okay.
You can see my video also, right?
Oh, no, I'm not able to see the video.
Oh, you're not able to see the video, but okay. Is it better to show the video, or how would you like?
Actually, both ways are fine, but some of the speakers they switch on their video also.
Let me. Yeah. Now can you? Yeah, can see, right?
Yes, very good, very good. Yeah,
Mm-hmm.
good. So let's wait for 5 to 10 minutes, and then we start our session.
Sure. So I keep my slides shared.
Yes, it is good. So
Okay.
actually, yesterday we got some issues with some speakers.
Hmm.
So they log in with two windows, and then it was mixing with each other also. So it is fine. Slides are
Okay.
good, and your voice is also clear.
Okay. Very
So
nice.
very good.
Very nice.
Also, we have Professor Raj Pulu Gurtha from Florida University. So, sir, are you there?
Yeah. I'm there. So is he after me?
Yeah, he's after you. Yeah.
Okay.
I'm
So
here.
if
Good morning.
hello.
Okay. So,
Good
Professor Raj,
morning.
are
Can
you
you hear
there?
me?
Yes. Okay. Okay, good morning actually here in the India. So uh, we'll we are on time, sir. So we'll start. Your talk is in the second actually after Dr. Nawab Singh. So please be online.
Sure. Thank you.
Okay, so I think there is a plenary talk is going to over very soon. So maybe we can start maybe in few minutes time. And those who are joining actually in that with the direct link, please switch off your mic other than the invited speaker, because your voice can be heard actually here. And rest of the people, they will be joining with the listener link. So of course they are not able to speak actually in this session. So if you have any questions, then please write to me in privately. So I will ask the questions. You should not ask your questions with the mic. I hope you all are very clear now, because yesterday also we followed the same thing. Okay, so I think we can start our session now. So, sir, are you online, right?
Yes, I'm online.
Yes, and your video is yeah. Now it is okay, sir. Okay, so let me introduce our first speaker for this session today. So let's welcome Dr. Nawab Singh. He's Director of Research Management at Institute of Electronics, A-Star, Singapore since January 2020. Prior to that, he was Director of Sensor, Actuators and Microsystems Program, developing MEMS technology platforms for IoT, industrial, mobile and AI applications, and Advanced Optics Program, driving flat optics to manufacturing based on 12-inch immersion lithography. So he started his career at IME in year 2001 as a senior research engineer with lithography process module. After working in semiconductor industry for 5 years, in a lifespan of about 19 years at IME, he cut through many technical departments and programs. For a period of 7 years as a technical lead at Nanoelectronics program, he developed highly scaled lateral and vertical nanowire gate all-around transistors, non-volatile memory devices, and high-efficiency solar cell, silicon solar cells. And as the outcome received George E. Smith Award 2007 for Best Paper in IEEE EDL, Singapore National Technology Award 2008 for his outstanding contributions to the research and development of nanowire technology platform, enabling the realization of ultimately scaled CMOS integrated circuits and new scale of electronic biosensors. IME Excellence Award 2009 for industry project developing surrounding gate transistor technology. and A-Star Talent Award 2010 for leading, educating, and nurturing talents. Okay, so in 2012, he was assigned to lead technology development for MEMS and later promoted to department director in 2014. Under his guidance, in less than 5 years, MEMS department engaged several top-tier MEMS industries and transferred 7 technology platforms, mostly of Piezo MEMS, to foundries for manufacturing. Regarding the education, he is graduated from the IIT Delhi with MTech degree in 1995 in solid state materials, and then pursued his PhD in NUS Singapore in electrical and computer engineering department. So while working at IME also, he has authored and co-authored more than 230 technical papers with a citation of more than 4,000 and H index is more than 35 in the top journals and conferences. And he has also filed 20 technology disclosures. So let's welcome our first speaker for his talk, and let's hope we all will get benefited with this. Okay, so sir, we're going to start. Thank you.
Raz, thank you very much for kind introduction, a long introduction, and invitation for the conference which gave me opportunity to present this wonderful platform, Lab-in-Fab. I think a lot of noise coming from your side, so you can move. Yeah, so this is a first of its kind for supporting MEMS innovators, a Lab-in-Fab model for accelerating adoption and commercialization of Piezo MEMS technologies and devices is very, very specific to piezoelectrics. So we are creating a center of excellence, Lab-in-Fab, inside a manufacturing fab. I will talk more in the later slides, and which will be open and will invite worldwide all the MEMS fabless startups, academicians, and students to explore with us. Move to the next. Okay, good. So I will start first giving some examples on the adoption and commercialization of the MEMS, how they have suffered, how they have, they have taken very long in the past, and what were the possible reasons of that. So let's look into the very early part of the MEMS development, which started, I would say, from this piezoelectric effect studied by Charles Smith in Bell Labs in 1954, and Honeywell developed a silicon pressure sensor based on that, which took about 2 decades in the development. Analog devices developed a monolithic accelerometer using MEMS middle process technology, for which the fabrication technology, in fact, started in Berkeley Lab in early 80s. And the product was out in 93. So although I put it 7 years here, this is in fact around 12 to 13 years. Agilent Technologies developed the FWAR device for filtering applications, very famous these days, for 4G, 5G, and all other communications, and which took about 2 decades to commercialize. Texas Instrument developed the digital micro mirror based DLP platform, the projectors, which took about 10 years. Let's look into the recent MEMS startups, which also take several years from founding to first products. And I mean, the time frame I'm talking is from founding, but they would have invested many more years before they found the companies to verify their concept. So give you some examples. Look at the Butterfly Network, which was founded in 2011, took 7 years to bring their first product, Butterfly IQ launch, right? This is a ultrasound probe. I think it's pretty well known using CMOS technology. Chip Microsystems, founded in 2013, took about 6 years, and its first device available in 2019. Vesper developed microphone company founded in 2009, and its first product was launched in 2017, 8 years. U-Sound, company known for speaker, developed first MEMS speaker, founded in 2014, and developed in the first product came out in 2019, took 6 years. And Polite, founded in 2005, and had a commercialization just this year of the first product. I believe this is inside Xiaomi phone, took 15 years. Here on this slide, the last 4 companies are all using piezoelectric with bottom to PGT, and Chirp and Vesper using aluminum nitride and scandium aluminum nitride. So let me provide you some of the reasons why commercialization has been slow. Is lack of skillful resources, lack of required infrastructure, work in isolation, gap between POC and industrialization, incompatible process flows, and tool sets. I think number 4 is very interesting part, where the startups are trying to verify their POC in research organizations or boutique houses and using tool sets and processes which are different from the manufacturing they are going to do later, and which is creating this POC partially incomplete. I wouldn't say useless, but it is making them incomplete, and a lot of work needs to be done, which is increasing a lot of time in industrialization. And also the incomplete POC data, the companies who are developing the product don't really understand the qualification criteria, which is only known in the manufacturing houses, how the industrialization goes. So the manufacturability and reliability concepts are missing when they are doing the POC. Substandard POC facilities naturally indicating to the research organizations. Slow POC due to limited resources and working hours, particularly the working hours at research organizations are, 6 to 8 hours or 10 hours. They don't work 24/7, while manufacturing houses work 24/7. Limited material choices for industrialization. You go to one research organization, you get one set, you go to another, you get another set, and maybe when you go for industrialization, manufacturing foundries, you don't even get the materials. So very limitations. Limited manufacturing knowledge in the boutique fabrication houses. The manufacturing knowledge, whether it's for MEMS or for anything else, all came from the CMOS, right? And these manufacturing houses which have CMOS and MEMS, both, I think, are very good in fabrication knowledge. Limited product knowledge and limited exposure to the applications are making the things going way longer. And to overcome these issues, we have created a Lab-in-Fab model where R&D is set up inside a manufacturing fab. You can find on these websites, this Lab-in-Fab is set up inside ST Microelectronics MEMS foundry. In fact, that's also a new setup in Singapore. You can see here the building, ST Micro's building, and second floor of this building is occupied for a large MEMS fab, and part of that large MEMS fab will be a lab. And the collaborators in the lab are A-Star Institute of Microelectronics and ALBAC. A-Star Institute of Microelectronics is collaborator as an R&D arm, providing more than 350 man-years of experience in MEMS R&D. So we are experts from material to the device characterization. You can look at material characterization, designs, technology platform development, and final device characterization, and even making modules, putting all the electronics together with advanced packaging options. ST Microelectronics, no doubt, bring more than 20 years of product development, industrialization, and manufacturing knowledge. I think there are no doubts to say that ST is tier 1 company in MEMS product development and manufacturing with 20 years of experience. And the products I highlighted in the second slide, the recent startups, majority of those startups are working with ST Microelectronics. ALBAC with more than 15 years of experience in developing, particularly I would say PGT materials, which are very high performance, piezoelectric material and also pyroelectric material. Pyroelectric, it has all the three properties, developing this functional material, and they have come up with many generations to increase the piezoelectric coefficient, reliability of the flow, reducing particles, and also increasing the breakdown voltage. So this setup, which is a 8-inch setup, right, will be inside of fab at Almaquio, bringing the complete skill sets required for any fastest development. Being manufacturing fab, ST Microelectronics runs operations 24/7, and we will have the first wafer in second quarter of 2021. So you can say about 4 or 5 months from now, and we are targeting the manufacturing to start in the end of 2022, which is less than 2 years. So now you can see from prototype to the manufacturing start is a very aggressive target. We are putting less than 2 years for our first product. And naturally, this piezoelectric center of excellence will bring innovative new devices in the area of AR, VR. You can think of maybe glasses, the scanners based on MEMS micrometers. You can develop the ultrasound probes for medical. You can develop 3D printers, and I think many more can be developed. And our focus in terms of material is starting from aluminum nitride family, aluminum nitride, scandium aluminum nitride, to PGT families and lead-free options like lithium niobate, KNN, and others. So we will explore all the options for long-term survivability of this Lab-in-Fab and creating impact in Singapore and to the MEMS community. So what would be the impact of this Lab-in-Fab is listed here. You can see that once the three parties are put together, we will have increased R&D bandwidth, which is not available anywhere today. If you go to IME, it's only IME. If you go to any research organization, they are all alone doing, right? Here, three parties are working together, so we bring a lot more research bandwidth. So you may see that the options available here in terms of technologies are much larger. We increase that. We increase POC speed because the working hours will be longer and the people will be more skillful, making less mistakes. Improve POC quality. Your proof of concept quality will be much better and closer to the industrialization, which will reduce the industrialization NRE. In place of your industrialization running for 2 to 3 years, when you move to manufacturing, maybe you will see in 12 months time industrialization completed. Naturally, the increased industrialization speed, when your POC is very close to the industrialization, product development supervision guidance is coming from ST Microelectronics particularly because they are not only the foundry, they are also a product development company. And Singapore also brings a lot of application partners on the table and help in early market capture to our startups. We are also looking at if we can offer a scholarship top-ups to the student, can provide them exposure and even the job opportunities in this Lab-in-Fab, and it will be open worldwide. Licensing opportunities for the MEMS innovators, who want to work together with Lab-in-Fab partners. If they are coming with innovative solutions and we find that suitable for developing a product, you get licensing opportunities. And we publish joint papers together for recognition. And we also look into grant funds from Singapore as well as from the outside. That's how we create the overall impact. Now I would show a little bit on the value proposition, the strength the three parties bring here. So I will start first from the ALBAC. As I said, for the last 15 years, you can see here they started in 2005 developing, and now they have 5th generation of the PET stack in 2020, which they talk about in terms of the figure of merit. The breakdown voltage multiplied by piezoelectric coefficient has increased to 6400 from originally 41. is more than 10 times, is nearly 15 times improvement. You can clearly see here the quality of the material from the XRD is very good. You can see the breakdown voltage, even for a micron-thick film, is about 200 volts, which is fantastic. You can see here the reliability, the mean time to failure is very, very large. They have patented technologies for not only deposition, but also etching of these films. And they are bringing both the technologies to Lab-in-Fab. The cost of ownership also, they're paying very serious attention on how to ensure that the PVP does not make the tool dirty faster. We don't spend a lot of time to clean up the tool, money to clean up the tool, and the failure between the processes. I mean, the tool down during the processes is reduced and particle count is reduced. And also paying good attention on the stress, which is less than 100 megapascal across the wafer. You can see here that we measured this almost 3D everywhere on the wafer, actually. And this is fantastic. It's much, much better than aluminum nitride and scandium aluminum nitride. Let me talk about the IME, which has a track record in developing process platforms and POC solutions, from materials to the device characterization. So some of the examples I put here, we developed with a partner a 2D micro mirror, and this was transferred to industry in 2015. You can see here how complex it is based on 3 wafer system, right? The top wafer having all these comps, and actually the top 2 wafers are providing the comb structures and a mirror, SAIN mirror, for moving in 2D, and bottom wafer is providing the interconnections so that you can apply the power. So it's a very compact solution. We developed energy harvester and transfer in 2017 to the foundry in Singapore. And this energy harvester is based on aluminum nitride. So let me tell you, so whatever work IME has done so far on piezoelectric is based on aluminum nitride and scandium aluminum nitride, except a demo work done with Allback, which I showed on the previous slide. And here you see this design, which was, not only for the narrow band, but even the broadband energy harvester, which was designed for low vibration amplitude of 0.2 G to 10 G with a vibration with a frequency range less than 1000 hertz in the low frequency, which are the common source of the energies available. And we generated power as high as 1 milliwatt per centimeter cube. The high power density was achieved. And this is again, you can see here a 3 wafer system: the top cap wafer, the central device wafer, and the bottom wafer. So we have the knowledge and the skill of how to handle these wafers, and here including the gather and vacuum inside with very hermetic bonding. We also developed this fingerprint solution for industry, which is running this in Singapore today as manufacturing pack. And this was transferred in 2016. We are currently working actually on RF solutions. So we have developed this platform which has thin film encapsulation. You can see here the center piece is the device piece, and top is the encapsulation. And then we are even putting the RDL layers on top to develop the passive component. We also developed a hydrophone device based on aluminum nitride. And this hydrophone device is being initialized today. We had run it in the field, and we are having a startup company on hydrophone. You will get to see that soon coming to market. So let me give you some example of scandium, the material development. I said IME is capable, and IME developed the platform from material all the way up to the device and device characterization. So here I show the material platform where we developed scandium aluminum nitride. Scandium aluminum nitride is a material which is better, which is higher performance than aluminum nitride, where the doping of scandium, is straining the bonds, is making the bonds longer. Actually, depending upon the A-axis is getting longer and C-axis is getting smaller, and end effect is the piezoelectric response with increasing concentration of the scandium is very, very significant. You can see here that piezoelectric response DT3, for example, is increasing 2 times, and which is providing you much better performance. But this material has actually a problem. Published earlier by other authors have a problem of these cone defects. You can see here. In fact, this picture is showing very few cone defects, and in reality, if you don't optimize the process, you can find very serious cone defects, and these cone defects can kill your performance. So you may find your performance as bad as aluminum nitride if you don't control, or even worse. And they also create the problem in etching. What are these cone defects? So in one of the papers we published, actually in IS 2019, we studied this, how the cone defect size is growing with the thickness. So we started with 200 to 1000 nanometers, and you can see here clearly that size is growing. And these are the cone defects very nicely, which are initiated depending upon what is your seed layer, what is your bottom layer, I mean at the bottom electrode, what is the first layer, what is the mismatch, right, in the lattice constant of this layer and the bottom, and how strained this layer is. For relaxing, these crystals are growing. So first we thought that these cones could be maybe some amorphous part, but no, this is a very nice epitaxial crystal with tilted grain. So you can see here it's tilted at 65-degree angle, and it's very nice. But once it is tilted, you know now that its impact on the device will be less. Now, so this area is contributing less because of the tilt into the device performance. So we have all the physical characterization capability. You can see here so nice PM analysis conducted. Then we started developing from the material platform to the device platforms, and we designed and developed the pyroelectric detectors. So you can see here a pyroelectric detector which is designed from 8 to 14 micron of the wavelength of the radiation. So you can use this for mid-IR gas sensing. You can use this for the temperature measurement for the human bodies, and even for imaging purpose. And this is the stack. We published this paper recently. Actually, it should have appeared by now in April. And you can see here that this stack is, the top layer is designed for absorbing and scandium aluminum nitride at 12% is used as a pyroelectric. Although we have now developed platform with 15 and 20%, but this is slightly older work. And you will see higher performing pyroelectric detectors very soon. And we designed this to control the warpace of the device. We put the ribs at the bottom, and these ribs made of oxide are very nice controlling the flatness of the device, despite the fact that scandium aluminum nitride and aluminum nitride are known to have the variability in the stress. And this device is uniform across the wafer. And you can see here the details of this device and the measurement. You can see here the output current, which is going all the way up to 1.99 nanoamps, right, with a square wave pulse here. And then we measure the dark current and various parameters. So if you have to look at the figure of merit, for example, the specific detectivity, we have achieved 6+ specific detectivity, which is an order of magnitude better than aluminum nitride pyrodetectors published by IEEE as well as by others. So clearly we can see an improvement, and also its NEP and responsibilities are better. Okay, so let me move now to the next application. That was pyroelectric property of aluminum nitride. Now we talk about the piezoelectric property, scandium aluminum nitride. And we designed and fabricated resonators as well as filters. So you can see here the F-bar resonator designs. It's exactly the same design. And then we fabricated in aluminum nitride, the scandium aluminum nitride. You can clearly see the SIF. The scandium aluminum nitride, the resonance frequency is softer because of the softness of the material. And the bandwidth of the filter is much, much higher. So you can see here from the table that bandwidth of this scandium aluminum nitride is about 174, while the maximum bandwidth we could achieve using aluminum nitride is 108. So it's a very significant jump. You will soon see the resonators and filters, including monolithic integration, coming out soon from IEEE. Now I will talk about our host partner, the ST, which is hosting this lab inside the fab, inside their own fab, right? The MEMS fab. Let me highlight here the MEMS fab. The good part of that MEMS fab is it's open for. Hello?
Yes, yes,
Yeah.
yeah, it is fine now.
I give some examples of how ST Microelectronics has developed, or what they have developed basically. As I said in my second slide, that there are recent piezoelectric companies who are working, and I give you 3 examples here. The chip microsystems developed this time of flight sensor with ST Microelectronics, and it has already reached manufacturing. So this is one of the reverse engineering approach. You can see here, chip and ST Microelectronics, and they brought this very quickly to the product. Although it was done, in isolation at ST Micro, and when IME and ST Micro and Albag work together, this will be much faster. The second product they developed is for U-Sound speakers, developed there at ST Micro. And the third one I highlight here is, this T-lens. This is based on a polymer, a lens based on polymer, where you are seeing this membrane being stressed using the piezo film, and then you make this polymer layer deform nicely, take a shape which is nearly aberration free, and providing a fantastic autofocus. I understand that this has already been used. It's already in Xiaomi phone. You may get to see, if you see Xiaomi phone, maybe it's already there. Yeah, you can see here how it really moves. I think that was my last slide. We surely invite you all to realize your dream. You can contact me, my email ID here, or you can contact IME or ST. You can just Google, press release from IME and ST, and can find more details and other contact informations. If you are a MEMS fabless, you are a startup, you are an academic or a student, anyone, right, want to explore, please reach me. Thank you very much.
Okay, so thank you very much for this introducing this very innovative, and I think it is very useful for especially for the Indian researchers actually, because mostly we try to innovate things, but we don't know how to really take it to the next level actually. So we have actually one more professor from IIT Delhi here. So Bhaskar, you would like to ask something, because this is very can be very useful for our students.
Yeah, Professor Nawab. So this is excellent. I think so. This is just the thing we need. I mean, especially the good piezo layers are very hard to find. I mean, a lot of times we spend so much time and energy kind of optimizing our devices, and it turns out the piezo film is just not good enough, and that lets it down. So I mean, just to get that is fantastic, and we would love to kind of. I mean, this seems like a wonderful opportunity for our students.
Bhaskar, well said. It is very difficult to get a good piezo layer. It really takes a lot of efforts to tune it. And we will explore how we can collaborate with academicians, how we can provide materials to academicians and students from this lab. And we will also look into how the student can, get exposure, can even travel sometime. We will look into all possible opportunities to collaborate and innovate and move together.
And we are happy to work with a fabless model as well. I mean, see, we have a small fab here. So a lot of times, I guess this was the model that I had thought about when I started here, that you use your small fab to figure out, the small kinks in the process and things like that. Right. But then when you really need a performance device, you go to TSMC or whatever who is giving us a MEMS process and get it done that way. So this kind of hybrid model works best, and I think this is just the kind of thing we need. I had a quick question.
Please.
Do you do any CMOS MEMS integration, like, or do you do pure? Is it a pure MEMS line?
No, we do MEMS CMOS integration. In fact, we have various kind of MEMS CMOS integration. Starting from PCB to advanced packaging, we have a advanced packaging line which at 12-inch, can bring the dies from MEMS, which are fabricated separately, and CMOS dies, put them together and integrate. So you could see them like a quasi-monolithic integration of those chips. It's possible. Even some of the devices, monolithic integration is possible, but I would say this chiplet concept, to bring different technologies together and do advanced packaging is a wonderful idea. I would like to propose that.
I think, so we are trying to do work in copper bonding and see if we can do, stacked chips, because usually the inductance of the wire bond is the problem. So if you can stack them up using this copper bonding, I think that's
wonderful. So actually, we had just yesterday started a consortium for die to chip to wafer bonding. We call that using hybrid bonding, where oxide and copper will be bonded, and will provide you a very low resistance and high density pitch bonding. So, and we already have hybrid wafer bonding, but wafer bonding is limited for same technology and same size wafers. The chip to wafer is a great concept.
Right.
Yeah.
Okay. Thanks a lot. Anybody else?
You're very welcome.
Okay, so I got some questions actually from the audience.
Please.
So first question is, how much did 3,3 coefficient change was observed in aluminum nitride after doping? Because you said like after doping you can change the structure and then it increases the D33 coefficient, right?
Yeah, actually it depends upon the doping concentration. So we had started with 9% doping and we had reached today 20% doping. We plan to reach all the way up to 30%. Actually, if you look at the data shown here, which is showing 5 times improvement at 40%, is very difficult to achieve in the manufacturing process because there are no targets available, which I would say alloy targets available, which can be used for manufacturing grade film deposition. So people do this kind of studies using co-sputter, using a scandium target, and using a scandium and aluminum target, right? And then deposit the film, which is good for R&D exposure. Right. So I would say that going the path from all the way up to 5 times improvement, right, depends upon the doping of the scandium nitride, and IME is currently at 20% doping. The curve shown inside that slide is pretty much correct.
Okay, so one more actually question from the audience is like, is there any piezoelectricity is reported for 2D materials also? Any?
I think the 2D material, I would say, is a very interesting area. But we have actually a research institute, our sister institute, IMRE, who are working on 2D materials. However, we have not figured out how to scale up those 2D materials. So we are not paying much attention into 2D materials because of that reason. Because our mission here is to scale up quickly, to make it manufacturable and develop the products. So I may not have the right information on that part today, but I surely can find and explore from my sister institute and update if you contact me.
Okay. So actually, I have maybe not a technical but non-technical. So how you said that you can give some top-ups to the students, right? So these students will be attached to joint student, or how this model will work actually? Because there are many students listening also this talk, so they may be excited to hear this.
Raz, is a very good question. I have not yet figured out. We need to work together with 3 parties, particularly the ST Microelectronics, who is the industrial partner here. in the time to come, I will explore further and work with the academicians to see how this top-up scheme works, even on university side and on the industry side. But I think there are opportunities where there could be a small amount dollars coming from industries and which can fund student scholarships, make their scholarship attractive, so we can attract very high caliber students working together to drive the innovation. But this is something actually we need to work out. It's not yet fully agreed and known. I think it will require a lot of discussions on both sides.
Okay. So thank you, sir, for your introduction of this innovative thing. I'm sure that this talk will be, because as the conference people say that this talk will be seen on the YouTube for 1 more week. So people around India or maybe around the world will be seeing this concept, and then they should be excited to explore the opportunities for their because we know that how we find difficulties in realizing the real product from our innovation. So let's hope it will help all of us. Okay, so thank you very much.
Thank you very much.
Thank you very much for this.
Bye bye.
So now in our session we can move to the next talk actually. So our next speaker is Professor Raj Pulu Gurtha from Florida International University. So he's a professor at biomedical engineering and also has a joint appointment with electrical and computer engineering department. So his expertise is in the area of packaging of electronic and bioelectronic systems, power supply, and wireless component integration in flex and rigid packages. So biocompatible packaging with high density feed-throughs. Also, he has a joint. So he's an adjunct faculty with Georgia Institute of Technology (ECE) department and Packaging Research Center, where he co-leads several technical thrusts in electronic packaging, working with the whole electronic ecosystems, which includes semiconductor, packaging, material, tool, and end user companies also. He is widely recognized for his contributions in integrated passive components and technology road mapping, and also for promoting the role of nanomaterials and nanostructures for electronic packaging applications, as evident through his several industry partnerships, invited speakers, invited presentations, and publications and awards. So his research led to 290 publications, which includes 80 journal papers, 14 book chapters, and 12 articles in various trade magazines, and more than 175 conference publications. He received 8 patents with several other provisional patents and intentional invention disclosures. So his papers also received more than 20 Best Paper Awards. So he has been a research faculty with GTPRC for 19 years, where he mentored more than 25 MS and PhD students. Also, he is editor for many journals, so that list is very long. So I'll not read that fully. So today he will be sharing his knowledge on heterogeneous system component integration with nano packaging. So let's welcome Professor Raj for his talk. And sir, thank you for sharing your time actually with this conference.
Good morning. Can you hear me?
Yes.
Yeah, thank you very much for this opportunity to discuss our research at the IEEE, which is a very prestigious conference. My presentation will be on heterogeneous system component integration with nano packaging. And I'm with Florida International University, Biomedical and Electrical and Computer Engineering. So I will talk about how this heterogeneous system integration benefits from nano packaging and can enhance power modules, RF communication modules, wearable and biomedical implants. So in each case, I will highlight how nanomaterials and nano packaging can enhance this heterogeneous system integration through the key elements that I show here. Components, mostly passive components and their 3D integration. So before that, let me again define what is packaging. Many people know what is packaging. Packaging is basically being able to connect devices, protect them, provide power, and be able to get data in and out. So and essentially system integration is packaging, it's hardware integration. So you can see its wide impact in almost all electronics. In power electronics, it's about wide bandgap semiconductor packaging using very low parasitic interconnections, thermal management, and being able to integrate storage components like capacitors and inductors. In case of RF and millimeter wave packaging, it's about reconfigurability, it's about integrating antenna and the whole front end in a single package to provide the highest performance and being able to have this multi-band communication systems. In case of wearable electronics, it's about also interfacing with the sensing interfaces and also being able to process the data, be able to communicate the data using this processing with various analog and RF. So in case of photonic sensing, it's about, again, connecting photonic chiplets, being able to amplify the signal, drive the photonic chips, and provide the data. So either way, if you look at it, it's all about interconnecting devices. It's about supplying power, providing interconnections for data and telemetry. So there are different ways you can connect devices. Traditionally, it's about packaging the devices individually and then putting it on a circuit board. That is what we all know, right? We all see it in any cell phone or even laptop. We see all these discrete components that are individually packaged and then mounted on the board. And the trend is how to connect the devices through embedding and direct fan-out interconnections, so that you can provide this same component integration with lower parasitics, thinner form factors, thinner modules, and be able to stack them one above the other. So there is no universal approach to the packaging. It's all customized. Sometimes it's about the it's about customizing for a photonic chip module where you are connecting the LEDs and diodes, and it's about being able to provide the power in some cases in a wearable system. In some cases, it's about a computing system, in case of portable processor. So there is no universal framework. It's all customized to different application segments. So, and hence packaging is not going to be a single format. It's going to be customized to different applications. So in the olden days, it's all about packaging discrete components and mounting it on the board. And then there is more and more wafer level integration of devices to provide the interconnections and be able to package the devices at the wafer level. And then the trend is to fan out the chip so that you use additional space around the fan out chip to provide more spread out interconnections. And eventually what we think is this fan out now goes to flex and panels, not just wafer fan out, but fan out at a flex and thin packages using very thin chiplets that are all interconnected. And that is where there is opportunity of how this can impact wearable devices or implantable devices, IoT, Internet of Things, and all kind of portable electronics too. So the idea is how to connect these chiplets when they're embedded and be able to provide those four things that we already said, which is interconnecting the devices, power, data, protection, hermeticity, and all. So if you look at the typical, now that we define system integration, if we look at where nano packaging plays a role, You need to bring a lot of components into the package to regulate the power, to deliver the power. You need to, for that you have a lot of high storage density components. That's where nano packaging can play a role, where you can integrate all these storage components. You integrate the heat spreader, thermal management, where nanomaterials like copper and graphene can play a role. You need to provide hermeticity using very thin coatings, ceramic or barrier coatings. And again, there is opportunity. You need to advance the dielectrics to not only provide low loss and high bandwidth, but also be able to provide other functions like reconfigurability. In the bioelectronics, you need low impedance electrodes, power and data. You need again have all this hermeticity, and very innovative connectors are needed for biomedical devices that need to be rematable. So there are a lot of needs in system hardware integration where nano packaging can play a role. So let me then, now that I just set the theme of the presentation, hardware integration with packaging, advancing it with nano packaging. Now I will just quickly go through what are the examples in power, in RF, and in biomedical. So I'll do it in the next maybe 10-15 minutes so that we can still keep the schedule. I think we are slightly running late. So in case of power, like, you need to deliver power to portable devices, and the power typically has to be converted to the optimal device voltage levels. And to do that power conversion, one is, you need to convert from high voltage to low voltage, 48 to 1, 3 to 1, or 12 to 1. So depending on the target that you have, the system. So you need to utilize this very high frequency wide band gap semiconductor devices. And that is going on fine, but where there are issues is now you need to still have the other components that go with it, like capacitors and inductors. So that I will talk in the next couple of minutes. So capacitors and inductors are needed because that's how you convert the power, regulate the power, and maintain the noise levels. And so if you do the power conversion on the board, on the circuit board, and then deliver it, there are a lot of problems. That's with efficiency, with granularity in the power delivery, and also in the whole thickness and form factor, the size of the system. So the trend is now, how do we convert the power within the package, right under the processor chip? So how do you bring the converter close to the chip? And to bring the converter close to the chip, you need to embed all these passive components, be able to still provide all the signal and power interconnects. And the passive component should be able to maintain that impedance at that current levels that you need to deliver. Similarly, same with inductors. So that's when you cannot use traditional magnetic materials or inductors. You can't use traditional dielectrics. You have to come up with new ways. So in the capacitors, the trend is to go to high surface area using either trench capacitors or dielectrics with, or even using porous electrodes so that you get extremely high surface area and then deposit dielectrics around them. In inductors, you need to reduce the coil length if you want to send more current. If you want to pump more current into the inductor, you need to use lower coil length, because otherwise the DC resistance will affect the power efficiency. And to do that, you need to introduce magnetic materials like shown here. And these magnetic materials need to be also achieving adequate power efficiency and permeability at the frequency that we are interested in, where wide band gap semiconductor devices work very well, maybe 10 megahertz and below and beyond. So how do you improve the magnetic materials? You need to go towards nanomagnetic films, magnetic films that are made with cobalt, nickel, iron, but with enough granular structure so that you can lower the coercivity, increase the permeability, and you also need to provide them with a layered architecture so that you can enhance the frequency stability without introducing eddy current losses. So these are the typical materials that are used today, flakes, magnetic flakes that are used to enhance the inductance density, magnetic sheets, or even sputtered magnetic films with thin oxide layers. And that is what we do actually in try to bring these magnetic films, but introduce these insulating films so that you can suppress the eddy current losses. So one approach is to bring these magnetic components within the packaging substrate using magnetic flake composites, like what we are showing in this case. This actually, what you see in this bright area has magnetic flakes. And now we are going towards very thin layered magnetics, but not the way people do with PVD, because physical vapor deposition creates a lot of problems in achieving the required geometry, and you need to have enough thickness to achieve the current handling and to achieve the enough inductance density. And physical vapor deposition gets into very costly throughput challenges that only semiconductor device companies that are dealing with very low current target can handle that. So for all the moderate and higher power levels, we actually are trying to use a different way of plated multi-layered magnetic structures. So that is about the multi-layered inductors. So now coming to the capacitors, trench capacitors are what the industry likes to use because you are now worrying about only silicon devices and silicon device integration in packages using fan out or even assembly, backside assembly or embedded assembly in the 3D architectures is pretty well established. But silicon, again, trench capacitors are becoming very popular, but where there is opportunity is using nano electrodes and dielectrics on the porous metallic electrodes, where you can get more surface area and achieve higher densities than what you can achieve with trench capacitors. So while doing that, we can achieve a few microfarad per millimeter square, and with thicknesses of about 50 to 100 microns. So that is really the need to deliver power. So if you look at capacitors, again, I bring a lot of topics, but I like to bring again, it's about nano packaging, it's about component integration with nano materials. So in this case, we are talking about power delivery, voltage regulator, and the filter capacitors are what we are trying to integrate using nano electrodes and conformal thin dielectrics. In this case, we are sintering tantalum nanoparticles, going very thin tantalum oxide, and then using thiophene P.PSS electrodes. We can make very good capacitors. So that is the capacitor integration. And the roadmap is shown here, where we are now going from silicon trench capacitors to porous high surface area capacitors, but achieving the same frequency stability, same parasitic resistance called equivalent series resistance, and hence that is the trend of integrating voltage regulators directly in the package. Now the next 10 minutes I'll talk about wireless communication for a few minutes and biomedical. But I also like to say before that in the 3D high power packaging, it's about putting devices on large copper heat spreaders, copper lead frame or copper carriers within the package. And this is getting very popular for automotive and other electronics, where you're trying to cool the high power gallium nitride chips with this kind of heat spreaders. And the key is now to use die-attached materials that are based on copper, nano copper, or graphene based materials, so that you can achieve better thermal management and dissipate the heat towards maintaining the required temperatures. And also at the same time, you also may need to deliver current through the same interconnections. So the next 5 minutes, I'll talk about how nanopackaging is impacting 5G communications. So I talked about power, now I'll talk about communications, and then I'll talk about medical devices. And so in this case, we are trying to bring in reconfigurability, trying to integrate antennas in the package with all this isolation and being able to increase the bandwidth by utilizing this stacked antenna and package architectures, the so-called stacked patch and patch antenna architectures. You need to be able to reconfigure them using either spatial or frequency multiplexing. So the key is to utilize again metamaterial structures to be able to provide the this smart reconfiguration. And again, this is where a lot of nanomaterials can play a role. So one way is obviously to miniaturize the antennas that only works at very, very low frequencies. So what we are trying to do now is to utilize more higher frequencies, millimeter wave bands. And the idea is how to bring components, tunability, reconfigurability, and the idea is again to bring in nanomaterials in the form of high-K dielectrics so that you can create miniaturized meta surfaces, metamaterial architectures. A lot of talks in this symposium on utilizing metamaterial architectures. I think there's a 5G session going on in parallel where there is the discussion about using metamaterials and also using magnetic materials for creating non-reciprocal components in the package. So the idea is to create these metamaterials, but we like to go beyond in also creating reconfigurability. So if you actually bring certain multiferroic aspects, for example, you had the plenary session today by Dr. Ramesh Ramurthy, where he was talking about using electric field to switch magnetism and so on. Similarly, you can use magnetic fields to tune the permittivity, but this has to be done at a bigger scale. RF doesn't work at 100 nanometers and so on. Particularly if you're doing electromagnetics, you have to deal with thick radiating structures, thick transmission lines. So in this case, obviously, you're dealing with 100 microns, maybe even hundreds of microns. But the inherent material structure can be designed to bring multiferroic aspects so that you can tune the magnetic field. You can tune the electric properties with magnetic field. You can create lenses, tunable lenses, reconfigurability, and so on. And when you go to 6G, the role of nanopackaging becomes even more important because now you have to not only provide meta surfaces with all this reconfigurability and to address the gain and other challenges, but you also need to provide very high bandwidth interconnections between the controllers and between all the CMOS, the drivers, and the radiating elements. So you also need to have along with these lenses and intelligent meta surfaces, you need to provide interconnects and waveguides, interconnects between the devices. So in this case, again, you have to have a high density substrate, like a glass substrate, and be able to provide the connections between these while providing the functionalities like with the other functionality that I just mentioned. And you need to be able to connect all these nanoscale devices. So if you want to connect these nanoscale devices, being able to provide this reconfigurability, tunability, and other functions, you need, again, nano packaging. And so I will spend a few minutes about where nano packaging can play a role in biomedical devices. So in biomedical devices, again, you need to reduce the footprint so that you can implant the device or you can put them on the skin as a very thin patch, almost as a disappearing electronics, totally unobscure and unobtrusive. So in that case, you need to have, again, be able to not only provide power, you need to be able to retrieve data and access the biological interfaces like neural interfaces, and be able to provide the whole functionality. Again, in this case, 3D heterogeneous integration becomes important, more important actually, because it's about, again, delivering power, retrieving data, being able to provide high reliability with reduced reliability issues, with reduced form factor. So we actually are working a lot on feed-throughs, telemetry, wireless neural recording, using these neural interfaces and being able to provide this 3D package integration, or what we call as nano packaging. So again, I just want to talk a few examples where we are trying to integrate a wireless neural recording system where you can implant or have a wearable device that doesn't need any power but does neural recording purely through RF backscattering. So you need this antenna interfacing with the mixing analog chip, which is the some kind of a diode or a mixer chip, and be able to backscatter that. And we build these very tiny wireless neural recording packages. Actually, there are very simple architectures to just record neural signal like ECG or even EMG or even implantable neural signals, where you just need antenna and a mixing element and a few matching, and it's completely passive. You don't need any battery, you don't need any power. And this again requires the ability to interconnect these RF and analog devices in a very thin flex using this nano flex materials, and be able to sandwich between hermetic ribbons. And that's where there are opportunities for nano packaging. And the next thing about it is how to interface with the biological system using very low impedance electrodes. So we are working on this graphene thiophene electrodes to improve the signal quality. But the key is actually how to embed the device and how to provide the interconnections to the antenna and other surrounding components. So if we can have matching networks, embed the diode chip, the mixing chip inside, and then have a very thin planar antenna. And that is where we have this so-called flex embedded 3D fan-out packaging for this very thin neural recording systems that are almost like a band-aid, like a patch on the skin, or a very thin implantable system. Similarly, we can put these thin implantable devices also on the skin or even around the spinal cord to record oxygenation, hemodynamics, basically blood oxygenation, to record the muscle activity, the recovery during spinal cord injury process, recovery process. So in that case, obviously, we are using photonic chiplets. You put a LED diode, you have to have driver amplifier, and we connect the photonic chip with the diode, the APD, and then on a very thin flex package. And now we are trying to deliver power using, this needs some power. You can't do it completely passive, like the way I did for neural recording. So in this case, you need to deliver power to power these LEDs, diodes, drivers, amplifiers, everything needs power, unfortunately, in this case. So we are looking at, again, new ways of delivering wireless power using inductive link. That's the most common way, everybody does that. But utilizing magnetic lenses to increase the inductive power transfer efficiency, but also using piezo-magnetic power telemetry. I think connecting to what was said in the previous talk by Dr. Nawab Singh, we can also bring in piezomagnetic structures implanted with piezomagnetostrictive coupling so that you can achieve very high power transfer efficiency. Unfortunately, again, I said that we need to deliver power. So because we don't want to use batteries and other things, the simplest way is to utilize this wireless power inductively, or using more recently using piezomagnetostrictive power delivery. So we also like to utilize these devices on the flex and also in the fabric textile. So what we think of is a hybrid packaging where we utilize these devices on a very thin flex substrate, but we provide connectivity to the textile because we need to have that connectivity to the electronics inside the textile because we have a big advantage. Textile have, several square inch. So you can have large antennas to harvest power. So if you utilize the textile electronics, then there is a lot of advantage because now you can communicate better, you can receive power because you have jacket with 1 square feet of area. So you can utilize that for harvesting and communication. And you still utilize very tiny chiplets to do the signal processing communication with the biological interfaces if you are wearing it on skin. So this textile to skin interface is what we are looking at using again flex hybrid packaging. We call it flex textile hybrid packaging. So we do certain things on flex because we get a lot of density. We do certain things in the textile because we get a lot of area. So we can, and the optimization is about how to partition between the flex and the textile and how to provide all these interconnections between the flex to textile using rematability so that you can reduce, you can remove and detach some of these devices during some parts of the operation, during some parts of the utilization. So we have electronics in the textile, we have electronics on the flex, and how do you connect them? How do you be able to provide rematable connections between these devices? So that is my summary, and this rematable is also important for implantable, not only wearable and flex. So what I'm trying to say is that there is device integration, that is packaging, and the device integration brings power, it brings data, it brings reliability, interfaces with biomedical systems. So for all this, you need to be able to provide these interconnections, advanced components, be able to provide thermal management if it is power in relatively high power systems, be able to provide bandwidth with reconfigurability for 5G and 6G, and be able to provide reliability with power and data telemetry for biomedical systems. So a lot of things that bring these electronics together, and it's all customized. Obviously, there is no universal solution. You have to optimize it for a biomedical system, optimize it for a wireless communication, broadband system, and also for a power. So depending on that, you optimize your hardware integration with all these nano packaging concepts. And that's what we do at FIU, playing in variety of applications, depending on the market drivers and customer interest. So I just want to highlight again that we have a very active team with a lot of students in Miami, and Miami is a great place for you to visit. Miami obviously is like a party place while we also do research. So it's a good thing for you to be here and partner with us. So we look forward to working with you. Thank you.
Okay. Thank you, Professor Raj, actually for sharing the idea. So it is very clear that when we talk about our devices or sensors, of course the packaging is something really important. We have to always think about, and then only the concept can be really successful. So if any of the any of this has any questions, actually you can directly ask, because I think I did not receive any in my chat box. Okay, so no problem. So basically, if you have any questions, then you can also email to the directly to the speaker. And as we are also a little bit running late in the session, so let's thank our speaker once again for his talk, and then we can move to the next talk. So thank you, Professor Raj, for your talk. Okay, so next we have oral presentation. So the speaker is Mrs. Megha Agrawal. So it's from CMTI Bangalore. And topic of his presentation is study on triple stack anodic bonding process for MEMS applications. So Megha, can you please share your slides? Also, Megha, your mic is off. Megha, we can still, we are not able to hear you also. So can you speak so we know that you are there? Hi, Megha, are you able to listen? Because we are not able to hear from you. Hi, Dharya, can you hear me?
Yes, sir. Sir, you are audible actually.
Okay, so I think Megha has some issue actually. Oh,
Sir, Megha has just now text. Okay, so.
okay. So Megha, can you speak because we are not able to hear you. Or maybe what I suggest is like she can log off and log in again, and in that time maybe we can start with the another next presentation, and then after the presentation Megha can start. So Manu, are you there?
Yes, sir.
Okay, can you share your slides?
Yeah, sure. Are the slides visible?
Yes.
So, good afternoon, everyone. So I'm presenting a talk on highly sensitive polymer micro mesh for measurement of vacuum in packaged MEMS devices. So this work is in
Manu, can
collaboration.
you come close to the mic because your voice is very low?
Okay, okay, sir. So am I audible now?
Yes.
So I am presenting on highly sensitive polymer micro mesh for measurement of vacuum in packaged MEMS devices. So this work is in collaboration with C4DFED at IIT Mandi. Moving on to the outline, I will briefly introduce the topic, how MEMS Pirani gauges work and what is the region of operation. Then moving on to the proposed polymer-based sensing element and what is the physics behind it. Then some initial simulation results. Then how the device can be fabricated using grayscale lithography technique, and finally following up with the conclusions. Starting up with the introduction, so MEMS Pirani gauge is a device for a pressure sensor for in situ vacuum measurement. So the device consists of a micro machined heating element which is exposed to the cavity whose vacuum level needs to be measured. Basically, these devices are co-fabricated with most of the MEMS devices like accelerometers, gyroscopes, bolometers, and microfluidic devices. So they are co-fabricated within a sealed package. This Pirani gauge will monitor the vacuum level at any time. So this heating element, the heat loss from this heating element basically occurs via three predominant heat loss mechanisms, that are radiation losses, gaseous losses through conduction through gas, and solid losses through the anchor points. Looking into the bottom right corner graph, the thermal conductivity versus pressure curve. Uh, this graph indicates that solid and radiation losses are basically independent of pressure. These are basically constant, and the predominant gas loss mechanism is the gaseous losses. So the Pirani gauges work in this transitional regime where gaseous losses vary in proportion with the pressure of the package. So these are an improvement over the traditional methods like helium leak test and Q factor extraction techniques, where these techniques are of low precision and highly expensive. And further, these are not suitable for real-time measurements. But Pirani gauges are, of course, low cost and highly sensitive and are suitable for real-time measurements with a typical range of zero point 0.1 Pascal to atmospheric pressure. So we propose a polymer-based sensing element revisiting this thermal conductivity versus pressure curve. The base limit of the Pirani gauge is depend upon the summation of these solid and radiation losses. But generally, the radiation losses are 10 to 15 times lower than the solid losses. So in this work, we neglected the radiation losses. Moving on to the solid losses can be given by the Fourier's law according to this equation. Previous research efforts have been made on the scaling laws, where we increase the length of the heating element, then while decreasing the width and thickness of the sensing element. So we are able to heat the suspended element according to the desired temperature with minimum power. And of course, these are also dependent upon the thermal conductivity of the heater material. So if we decrease this, if we use the lower thermal conductivity material, we are able to decrease the base limit of the Pirani gauges. So that is where the SU8 based sensing element comes into the picture. If we look at the thermal conductivity of SU8, it is around 0.2 watt per meter Kelvin, which is almost uh, 10 times lower than the silicon based Pirani gauges. Around silicon nanowires have been reported for Pirani gauge applications, but the thermal conductivity of silicon nanowire is around 65 watt per meter Kelvin. So comparison to silicon, these are the SU8 is a extreme lower thermal conductivity material. So it is able to.
Manu, can you somehow come close to the mic because your voice is still very low.
Okay,
With the
okay, right, sir, right,
with the
right.
full volume, it's still very hard to hear you.
So basically, this extreme lower thermal conductivity material is beneficial for slow heat dissipation through anchors. So it will ultimately decrease solid losses while decreasing the base limit of the gauge. Ultimately, it will increase the sensitivity of the device without incurring extra power consumption. So this is the structure we propose, the SU8 based membrane micromesh structure. Uh, First, the SU8 based membrane is suspended over the silicon SiO2 substrate, and the suspended membrane thickness is around 5 micron with a width of 3 micron. The whole membrane area is around 40 micron cross 40 micron. As you can see from this legend, the maximum temperature is around 190 degrees centigrade, and the temperature across this membrane is uniform as depicted from this simulation results. Looking at the 3D graph at A, the graph shows the 3D temperature profile over these suspended membranes along this direction. Uh, and if we can look at this graph, the temperature is almost uniform over the entire structure. While it decreases at these points, these are basically probed areas where we probe the constant current at the structure. Moving on to the this lower graph on the left bottom corner, this shows the temperature profile along the thickness of this suspended membrane, this 5 micron SU8, and over to it there is a thin platinum film. We can see that this pink highlighted portion, the temperature is uniform along this platinum element while it decreases to around 0.15 degrees centigrade along the thickness of SU8. So which is very actually negligible. So we can say that the temperature is uniform across this whole membrane, which is actually a good thing in case of Pirani gauges, as we get uniform temperature and of course the high sensitivity. Then the graph in the C shows the temperature distribution according to the different input power at T1 and T2. These linear curves show that basically the temperature profile is constant for a typical value of pressure. So it has been plotted over the entire pressure range from zero point 0.1 Pascal to atmospheric pressure, that is 10 raised to power 5 pascals. And the graph D shows the slope of this each linear curve. So basically the yellow highlighted portion is the operating range of the Pirani gauge, where thermal impedance linearly varies with the applied pressure of the cavity. So with this micro mesh, we are able to successfully detect the pressure from 4 Pascal to 10 raised to power 4 Pascals. Moving on to the fabrication, how the structure can be fabricated. So the structure fabrication is a single lithography process, and it is fabricated using a grayscale lithography technique using a single mask. So the mask design is shown here. Although this mask design is not in accordance with the simulation, but we just initially fabricated a prototype device for proof of concept where the UV light is exposed with full intensity at these anchor points, these 4 anchor points. While where we require the suspended membranes, the luminous intensity is around 130, which allows the UV light to partially expose the photoresist. That is our polymer SU8. Moving on to the fabrication process, the first step is the coating of SU8 over the silicon SiO2 substrate, and the UV light is fully exposed at the anchor points according to the mask design in our first process, and it will partially expose the SU8 over the suspended areas. Then after developing the SU8, we get the desired structure. The desired structure is then vacuum annealed at around 300 degrees centigrade. After then, a PMMA is drop casted at the edge of the wafer so that it will entirely spread over the whole wafer, but its thickness is below the SU8 membrane. After that, a thin layer of platinum is evaporated over to that PMMA, which is finally lifted off to get the desired pattern. So basically, the role of platinum is to make electrically conductive connections from which we can heat the suspended SU8 membrane, because SU8 is not electrically conductive. So using platinum membrane, we can heat the SU8 membrane. And this is the graph, this is the fabricated structure. And these are the SU8 membranes, and the shining portion is the evaporated platinum film. And the structure is made according to the 4-point configuration so that we can get accurate results. Finally, concluding the talk, the fabrication of the device is quite economical, simpler, and can be fabricated using single lithography. And the operating range of the device is from 4 Pascal to 10 raised to power 4 Pascals. And the extracted sensitivity of the device is 235 degree centigrade per milliwatt per decade Pascal. And this number is quite good because we are getting almost 100-fold increase in sensitivity as compared to the state-of-the-art silicon-based Pirani gauges. And of course, the power consumption is because if we look at this simulated figure, these temperature profiles are plotted at 56 microwatts. So the power consumption is also very, very low. Finally, the SU8 as a dielectric membrane offers increased sensitivity without extra power consumption. And also the hard baked SU8 is a very, very good mechanical, it also provides very good mechanical strength to the platinum film. And but the actual fabrication device is still under process at IIT Delhi. We have only fabricated the prototype structure. So finally, I would like to acknowledge the Center for Design and Fabrication of Electronic Devices lab at IIT Mandi and NRF and CRF at IIT Delhi, and the financial assistance from IIT Delhi. Thank you for your attention. Any queries are welcome.
Okay, so thank you, Manu, for your presentation. So, is there any questions? Because I did not receive any in my chat box. So, if you have any questions, maybe you can ask directly to Manu, and you can write email or something, and he will be happy to answer. And okay, so we can go. Yeah, so we can, or you can write to me also. Then I will be happy to answer your questions. Okay. So okay, we can move to the next talk because we are running 15 minutes late in the session. So now I think Megha can actually start, because I think there was some problem with her mic before. So Megha, can you share
Hello?
your screen now?
Am
Yes,
I
yes,
audible now?
yes, we can hear you
Yeah.
now.
Thank you.
Okay, so Megha is from CMTI Bangalore, and her topic is study on triple stack aerotic bonding process for MEMS applications. So Megha, you can start your talk.
Yeah. So wafer bonding is mainly used for temporary or permanently join two or more wafer using different various parameters. And there are so many bonding techniques are there. It depends on whether we are using any intermediate layer or we are not using any layer in between. So if we are not using it will be two bond chucks, top and bottom. Heating chucks will be there. Some tool pressure will be applied and chambered, some pressure will be there. And the electric field, especially in the case of anodic bonding. So here, out of these bonding processes, the anodic bonding is mainly popular for glass to silicon direct bonding. It is also called field assisted of and if you see the major sector in the MEMS, it is mainly for accelerometer and gyroscope. And few type of MEMS accelerometer and gyroscope demands for the triple stack of silicon and glass wafer. Here is an example of triaxial accelerometer, and we can see here it is the requirement during fabrication to stack. Focusing on this. And anodic bonding, if we talk, it is mainly first introduced by these two scientists in 1969. And they have used these techniques mainly to join metal and glass surfaces. So the anodic bonding is the process in which on temperature, high temperature between the range of 300 to 500, if
Megha, Megha, let me interrupt you. So can you only share your work basically, because you know the introduction is already I think most of the people know already. Please share your work. Yeah.
So triple stack bonding setup, there are two types of setup, 3 electrode setup and 2 electrode setup. So in 3 electrode setup, generally all three wafers, whichever we want to triple stack, all will be separate contact will be there. And in 2 processes approaches I have used here. One is single step process, another one is 2-step process. In single step process, all three wafers were loaded together, and the polarity of the voltage, whatever is applied, it will be reversed, inverted through the during recipe. And in first approach, that is 2-step process, in that one wafer is stepper foil, that graphite foil is conductive and flexible. So as the tool will come down, this is the graphite foil is flexible enough, and the center wafer is greater than the silicon wafer. The graphite foil will touch the glass wafer, and the polar voltage will be applied on the glass in place of this top silicon wafer, and the bonding will happen between glass As I have explained earlier, all three wafers, silicon, glass, and glass, silicon, glass, are loaded together and bonded using the reverse polarity concept, like 400 minus 400 in this way. And so, using both approaches, the wafers all triple stack bonding has achieved, and the further characterization. So these are the characterization results. The bonded wafer are further diced using diamond dicer to see the interface image of the bonded. All samples using both approaches are done and are successfully diced. After this, the interface and optical microscope images are captured. So these are the images using both approaches. And further, the strength of these bonds is characterized using die shear test. So the stacked die are bond. Similarly, in the case of glass, silicon, glass, and if you will compare between glass, silicon, glass, and silicon, glass, silicon, the strength is better in both for both approaches. In the case of glass, silicon, glass, since silicon is better conductor than glass. So these are some bond shear strength graphs. So this I will conclude in both. Anodic bonding of triple stack for bigger wafers also, and even the both approaches are good for bonding the triple stack, but it is observed that second approach, single step approaches provide the better strength. Further EDEX and other analysis will be done to see the sodium contamination and other things. So with this I will.
Okay, so Megha, I have few queries actually.
Yeah.
So, what is the wafer size actually you bond together? This glass and wafer.
Right now I tried just 10 mm by 10 mm. And
Oh, so
the
it is chip level also.
yeah, chip level.
So chip level, and how big wafers you can also bond?
Uh,
6 inch. So what is the system? Can I know?
SAS Microtech SV Gen 2 system we have, and we have the bond
Okay,
aligner
okay.
also
So,
from SAS. Yeah, MABA6. Yeah.
okay, so basically, maybe I'm a little bit not aware of this CM TI Bangalore, right?
Sure.
So
I
is
will
it like,
share the link. I will share the details, brochure, and soft copy, and other things with you. Sure.
let's say if we would like to have bonding also to be performed at your place, so is it possible? Let's say-
This mode.
Okay, okay. So do you also So you also do active research at your place, or is
Yes,
it like
sir. Active
a
research is there. I am working as a scientist, and we have a team, and this project is recently facility has come up, and we have started the research in other fields also, mainly especially for 3D integrations of advanced packaging. Yeah.
okay, that is very good. Okay, so if because I did not receive any questions for this, so maybe if you have any questions, you can please ask directly with Megha. Okay, so thank you, Megha, for your talk. So now we have, yeah, so now we have the last presentation for this session. So the person with us is Harsha S, and the title of presentation is Electrochemical Deposition and Characterization of Copper Pillar Bumps, and the application is towards the flip chip bonding. So let's welcome our last speaker for this session. Okay, so can you please share your slide, Harsha? Harsha, are you there? Okay, so I think there is some technical issue is there. So let's wait for some time, because this is the last talk of this session. So uh, can you? Harsha, I think there is problem with your login. So can you just quickly log off and then log in again? Because for Mega also it was a problem. Hi, Harsha, can you hear us? So if you can hear me, can you please log off and then log in again? Because I think there is some problem actually with your login or something. Or maybe if you and Mega are actually using the same laptop, so can you log in from her laptop or something? Hi, yeah, I can see you actually now within different login. So can you hear me?
Hello, am I audible?
Yes, yes, yes. Please share your screen now.
Okay, just a minute. Sorry about the logistics issues.
Yeah. So until you log in, so let me introduce Harsha Jagdish from CMTI Bangalore. So title of the presentation is electrochemical deposition and characterization of copper pillar bumps, and the application is towards the flip chip bonding. So let's hear from him now.
Thank you for the. I believe the.
Yes, we can see now. Please go ahead.
Very much. So, as introduced, I am Harsha Sanjeev. I work at Center for Sensors.
Yes, please go ahead.
Targeted towards flip chip bonding application. So the outline of my presentation will include overview, methodology, experimental details, results, and conclusion. We were targeting to have a fine pitch flip chip assembly in order to minimize the footprint area of any sensor or a MEMS device. So having to the substrate preparation, where we have chosen a 6-inch silicon wafer, piranha cleaning for 20 minutes, 120 degrees. We had a titanium coating against chromium coating, which we generally see in literature, for about 20 nanometer, and we used an electron beam evaporation process to deposit this titanium coating, and over which we had a gold coating of 15 nanometers, again using the same process. This of 100 nanometers. I'm sorry about the error there. It's 100 nanometers using electron beam evaporation. So the process flow, what we followed was we coated the silicon wafer with a seed layer, and we used the resist AZ9620 for the spin coating. Generally, because the thickness of the pillars, what we are aiming at is chose selective electroplating of copper and followed with photoresist stripping and metal etching in order to achieve the fine pitch bumps, which are the substrates for our flip chip bonding application. So generally, the design parameters or the applications that we selected was using DOI. We chose experiments. Practically achieving it following the exact similar steps resulted in literature or reported in literature is a tedious process, and we have seen that it is not practically possible to replicate the same results because the environmental conditions and the raw materials that we will be using will be different. So in order to gain confidence, we had chosen a higher diameter, and copper pillars to a height of about 17.3 microns as shown in the graph, and the SEM of the electrodeposited pillars are also shown here. This is after the PR stripping. So in order to continue with the experimentation, we reduce the diameter of the pillars to as low as 10 microns, and we also of which unique design almost similar to what we achieved earlier, but we had to do minor modifications with respect to duty cycle and the on time and off time of the experimentation. So the results of the experiment 2 are indicated here. As you can see here, the height deposited was only 10 microns, and this was with scale of about 25 micron. So all these experiments resulted in the establishment and optimization of practically growing copper metal through electroplating deposition route, and targeted copper pillars of 10, 20, 30, and 40 gaps were very successfully achieved, and there was no overflowing or any shorts which was observed. We also characterized from electro deposition. The pre-processes targeting these three were successfully achieved. We have also continued our work with respect to minimizing these diameters and the gaps for about less than 10 microns now. And we are seeing positive results there as well. And that's the conclusion of my presentation. I would be happy to answer.
Okay, so thank you, Harsha, for your presentation. So I have a question. So basically, this flip chip bonding. Okay, so it is nice results shown that all the bumps and there is no overflowing is there. Everything looks good. So
Yes.
have you really tried this packaging for a real device? Let's say to integrate the real device to the through this packaging.
Laboratory in Delhi SSPL. We have done that successfully. This work as part of the process establishment was done on developing substrates which are necessary for the experiments. These were not, the reported work here is not of the actual devices. It's of the substrate which were developed solely for this purpose.
Okay, so actually, again, because I'm from IIT Delhi, and sometimes let's say if let's say I'm curious that like if some of our device needs this kind of packaging, right? So if we want to collaborate with your institute for this processes, so are you open for the outsiders for the collaboration, or how is it is going on?
Yes, very much open for collaboration and research work, or in terms of services mode also. And we would be
Okay, okay.
happy to have.
Okay, so very good. So we at least with this talk and the previous talk, we came to know about the capabilities available at your center, right? So thank
Yes.
you very much. So I did not receive any questions through chat. So let's thank our speaker. And if you have any questions, you can directly ask, email to them basically, and then they'll be happy to reply you. So thank you, Harsha, for your talk. And
Thank you very much. Thank you for having us.
with this, we can conclude our session also now. Our next session is starting at 1:30. So I hope you all will be joining. And that will be the last session for this MEM symposia of this conference. So thank you, everybody. And now with this, we can conclude your session.
Hello, Sushil, can you hear me?
Yes, sir.
Okay, good. Pushraj, are you there?
Yes, I'm here also.
Okay, great. So, I think Professor Nathan is also here.
Yes, I'm here.
So, how's the situation there in Delhi, Pushraj? Are
Inside
you
IIT
attending the
is good,
labs?
but if you follow the newspaper, is very bad.
Yes, no, but what is the real situation?
No, what?
I mean, what is the real? Because we are also going through the
No,
media report only.
that's what I'm saying. Like inside IIT is very good. So we are almost all the
Okay.
PhD students are back here. So
Okay.
like research is fine. I'm saying research is fine and teaching is going online. So that is also not bad.
Okay.
But outside, like, there is a sudden because one more thing is there is a pollution was there, but luckily pollution is now improved
Yes.
because
Mm-hmm.
the wind speed is quite good nowadays. And another thing
Okay.
is, we also then winter season, then and the mostly this is a marriage season actually. So a lot of marriages are
Yeah.
going on nowadays. So that's why a lot of people are going, joining big groups here. So I mean,
Let's see. Yeah,
yeah.
certainly. Yeah, yeah, let's see. So, Professor Nathan, can you hear? I think he's muted.
Yes. Yeah, I can hear
Yes,
you.
how are you? Yeah. So, how's the
Good.
situation at your side?
We're kind of everything shut down, so we're teaching all online and everything. So
Online, yes. Okay, good. Yeah, we are really hoping that this whole thing will settle down soon because all the students are
yeah,
really now irritated and tired. So earlier they
yeah,
were happy that they had got a chance to visit their families, but now after staying almost 7, 8 months, they are all tired now. They are coming back
yeah,
to
yeah.
these things. Yeah. So Sushil, one of the participant, she is going to present her seminar through the recorded lecture, right? Sushil, can you hear me? Okay, let's see. Just give me 1 minute.
So, Professor Dixit, how is the situation in Mumbai?
Mumbai, I mean, like it's the same story as IIT Delhi. So inside the campus, we are having some cases. Okay, so every week we are getting about 4 to 5 cases. But
Okay.
situation are in general is in good control. Okay, because IIT hospitals are fully like right now available to others. And outside, if you go to outside, because there's of a huge population, there people are not really following kind of a rules. That's one of the major issue. But inside campus, it's still okay. So we have started calling our third year, fourth year, and fifth year PhD students. So they are back in the campus, and we will take a decision like how to call and when to call all the undergraduate student. Okay. So
Okay.
Pushpraj, so shall we wait for some more time, 5 minutes, and then start, or what is your
Yes, yes, yes.
recommendation?
We have to little bit wait for 5 minutes because so usually like what you have a link, right? This is a direct link. So direct link is like now when you speak then I can also hear. But most of
Okay.
the participants are they are having a listener link only. So
Okay.
those people I think you cannot see here actually. So they will be just browsing through and then there is a YouTube link.
Okay.
So they can also only
Okay.
see
Okay.
that. So
Correct,
let's wait
please.
for
Correctly.
5 more minutes and then we can start.
Sure, sure. So just give me this signal, and then I will introduce Professor Nathan,
Yes.
and in a couple, and then he can just begin. So we have about, I believe, 30 minutes of presentation and 5 minutes of question answer, or is it 25 minutes of presentation and 5 minutes of question answers?
And that is flexible. So
Flexible,
basically,
okay.
let's
Great.
the target is only to finish within half an hour. That's the
Oh,
only.
okay. 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 Great. So Nathan, are you primarily working in the area of this piezoelectric transducers, or also the
Yeah,
packaging
yeah.
side?
Yeah, so I work in piezoelectric MEMS, and energy harvesting is one of the big areas for me. But yeah,
Okay.
I do other things, microphones,
Okay.
aerosol generators,
Okay.
yeah,
Okay.
yeah,
Okay.
all types of stuff, yeah.
Yeah. So I had a
But
little bit of
MEMS in
experience.
general, yeah,
Very nice. Yes.
yeah,
So before joining IIT Bombay, I was in Finland, where in VTT, there's an institute called VTT,
yeah, yeah,
and
yep.
yeah. So my team was in this MEMS fabrication and packaging and the aspects.
Yeah. Very good.
So it is exactly 1:31 now. So let's wait for 4 more minutes. We will start at
Okay.
1:45.
Okay. Okay. Sure.
Schedule is quite tight because we just ended our earlier session at 1 o'clock and only half an hour was there for that. So this is a problem.
Yeah. No,
And
no,
they
this is
are
fine.
there are 8 to 9 parallel sessions are going on. So
Okay.
let's wait
Okay.
for 3 4 minutes and then 1:35 you can start actually.
Okay. 135. Okay.
Sir, for your kind information, we have one oral presentation in the pre-recorded mode. So
Okay.
okay, so the technical team will be the run the video on that time.
Okay, fine. Okay, that's fine. Okay. So Pushpraj, I think I should begin now.
Okay, so maybe before we begin, so let me introduce Professor Pradeep Dikshit first. So
Yeah.
we have Professor Pradeep Dikshit. He will be chairing the session actually now. So he is a professor at Department of Mechanical Engineering, IIT Bombay. So I just give this short introduction. He's working in the area of MEMS, micro system packaging, 3D interconnects also. So please take over actually.
Yes. So thank you, Pushpraj. Okay. So I am Pradeep Dikshit from Department of Mechanical Engineering, IIT Bombay, and I will be chairing this session. So in this session, we have four presentation. Two are the invited one, and the two are the presentation by the PhD student. So our very first speaker is Professor Nathan Jackson. He's a faculty in Department of Mechanical Engineering in University of New Mexico, USA. So Dr. Nathan has joined Mechanical Engineering Department in 2017 after spending about 8 years in National Institute in Ireland. He has an extensive background in these novel smart materials applicable in MEMS applications. Currently, his group is focusing mainly on the applied research that can be transferable from lab to the real life application, which includes IoT application and biomedical. Okay. Primary interest of his group is on the piezoelectric materials, vibrational energy harvesting, acoustic resonators, flexible and stretchable electronics, and biosensors. Professor Nathan is a senior member of IEEE and a finalist for Inventor of this year in ICT in Ireland. Okay, so let's welcome Dr. Nathan Jackson, and let's hear about his presentation on this piezoelectric materials. Dr. Nathan, chair is yours now.
Okay, thank you. So thank you for the invite. So I'm sharing my screen, so hopefully everyone can see it. So thank you. So I'm Nathan Jackson. I'm from the University of New Mexico, and my presentation today will be on really a high-level overview of the challenges that we face in MEMS energy harvesting, with a focus on piezoelectrics, and then I'll go through some of the current methods that researchers around the world are trying to solve these challenges, and I'll talk about our research in particular, how we're trying to solve it. Next slide. Okay, you've already given the introduction, so I'll skip kind of my experience and background in the area. So first, for the outline of the talk, I'll give a brief motivation for why we're interested in energy harvesting, especially at the micro scale, and some background on what we've accomplished at the micro scale. Then I'll go through the heart of my talk would be on the challenges and current solutions of how people are trying to solve these problems. So there's numerous challenges, especially when you go to the micro scale for energy harvesting, such as power density, bandwidth, frequency tuning, reliability, packaging, and then application-specific designs. So I'll go through sort of these different challenges in my talk. So the first question that we ask is, why are we interested in microscale energy harvesting? And this can be answered in sort of three words, either the Internet of Things or cyber physical systems. So we live in, a time where we want information on everything and everywhere. We want to know, okay, our structural health monitoring of our bridges. We want to know, information on smart buildings, humidity, temperature. We want smart roads. We want sensors for agriculture. We want to know basically information on everything. And how do you get this information is through usually wireless sensor networks or wireless sensor nodes. And all these different wireless sensor networks or nodes, they all have different sensors depending on what they're trying to sense. and they all have a communication system, a processor, memory, but they all have power. They all require power. All these devices require some type of power. Right now, these are powered by batteries. But this is difficult in remote areas or difficult to reach areas where you have to change the batteries. A simple thing as a battery, changing a battery could cost a lot of money or be also not very easy to get to, like say at the top of a bridge or a building, or even inside buildings, like embedded in buildings. Where you'd have to tear down the walls in order to get them. So we really want to create a self-sustaining system that doesn't need to have these batteries. They can just operate for long periods of times, lifetimes, 20, 50 years, without any need for a battery. There's many different methods of energy harvesting. You have photovoltaics, you have electromagnetics, you have thermoelectric. But what we're interested in is kinetic energy here. And now these energy harvesting devices, they're not simply just energy harvesting devices. You also have to have power management circuits. You have to have AC, DC rectifying circuits, DC to DC, sometimes voltage boosters, so all these type of things. My talk today will be focused just on the energy harvesting part, but I just want to acknowledge that ultimately what we want to do is have something like this. We want to have something that can replace a battery. And you also need storage, I should say, too. Yeah. So for kinetic energy harvesting, there's 3 or 4 different methods here. I showed 3 of them. The most common ones are piezoelectric energy harvesting, electrostatic, or electromagnetic. There's also triboelectric, which is gaining more interest in recent years. Now, all these have their advantages and disadvantages. My work focused on piezoelectrics, but a lot of the challenges that our talk about today actually apply to both electrostatic and electromagnetic, as well as triboelectric. So the challenges that I'm going to talk to you today about, like I mentioned in the outline, are going to be on power density, which is sort of these kind of go in order of like where the most common ones that people are trying to solve. So power density is one of the most common methods that people are trying to solve. Bandwidth is another one. Frequency tuning, which kind of works with bandwidth, trying to tune the frequency of the device to match the source, the frequency of the source. Reliability, I'll talk about a little bit. This is one that's often overlooked in academia, especially looking at MEMS packaging and stuff and how to make these more reliable. So I'll briefly touch on this, and then I'll touch on application-specific designs. So one of the first things is power density. So obviously, when you're making these devices, that you have to meet a certain specification of power density. If your device can't harvest enough power, then to power your wireless sensor network or your node, it's not very useful, and it's limited in its capacity. So you always want to make sure you can have high power density. Of course, we're always working with electronic people to try to for them to reduce the amount of power consumption that they need, so that way hopefully we can meet somewhere in between. But one of the problems with power density, especially when you go to the microscale, is if you look at the laws of scaling, things don't scale down linearly. We can't just take a big like wind turbine, and shrink it down and get the same, sort of power density at the smaller scale. It shrinks down nonlinear. So this makes a big problem for microscale devices, as we're often talking about, in the MEMS area, we're talking about making things in the microwatts to even, up to maybe 100 microwatts of power per device. So that's one of the big issues, and that's shown, here in this figure to the right. You can see where a lot of people, a lot of different researchers, are getting very low power densities, under nanowatts, power, and this is voltage. So you really got to get sort of high voltage, so that way you don't need voltage boosters. but also high power density, and there's only, certain people that have gotten this high power density or in this area that need to actually get enough power to supply for a wireless sensor network. And one of the big challenges first with power density is, how do we define power density? So if you read, 20 pages on energy harvesting, MEMS energy harvesting, or even energy harvesting in general, kinetic energy harvesting, you'll find that almost every author has a different definition of power density and what they report. And this is the challenge. And I'm not going to give you the answer because I don't have the answer which one's the best. But I'm just pointing out some of the problems. So a lot of researchers point out they just give the power. So how much power their device can generate. Of course, this depends on size. So that's why power density is important, because if you have a 3-inch, piezoelectric, say, cantilever beam, that's going to generate more power than something that's going to be, say, like 500 microns in length. So you really need to look at power density. But then how do we define power density? The definition of power density is just, power divided by the volume. But what do you use for the volume is the big question. Some people use the volume of their beam, say a cantilever beam, so they might use width, thickness, length. And that's sort of the standard. But then some people maybe they don't use the thickness of the mass, because a lot of these, we have to have a huge mass at the end in order to get to low frequency. So that, they use maybe the dimensions of the beam, but maybe not the mass. Others might include the better way is actually if you can include displacement. So a lot of times, like the end of our tip of our cantilever might be displacing 3 millimeters in one direction, so maybe a total of 6 millimeters. Well, if you're taking power density, you really should take into account the overall dimensions of the overall movement. But this is often not done in most papers. Most people just use the dimensions of the beam. Then there's other people that choose power density per acceleration. So a lot of these devices operate at low acceleration, say 0.1 G or so. And so then they put it in per acceleration, because then they can, then they basically increase or enhance the number that they're showing to give, to make it look like they're actually harvesting more power than what they actually are. And then other people, even to make it even more complicated, they do power density per acceleration per thickness of the piezoelectric material. Because again, if some people are putting down, say thick PZT material, and then some people are putting down thin film aluminum nitride or zinc oxide material. So they try to, basically they use the units that make their data look the best. And that's not really it's hard to compare, devices. And it is, I've read a bunch of papers and review papers, and it's very difficult to compare these different devices because everyone uses different definitions of power density. And then there's even a specific case where you have high impact, or special cases where you have impact or shock based applications. For instance, we worked on harvesting energy for a pacemaker, which a pacemaker is not a simple sinusoidal vibration. It's a beating. So you have a 1 beat per second. So then, when we were writing our papers, some reviewers were like, okay, what's the power density? And it's like, well, what do you consider the power density? Do you want the peak power, the power density, using the peak power, or the power over a certain amount of time? And so, there's always inaccuracies, and makes it difficult to determine what people mean by power density. And a lot of times people would put, in this case, they would put the peak power. So, but that's not really, when we wrote our paper, that's not what we did, because again, what we really want in the end application is what's the power over, say, a second or 2 seconds of time, because that's the average power that we're actually harvesting, not necessarily just the peak. So how do people get around, how do people solve the power density? So the first method is to, choose the right material. Now, what's the right material? there's not a simple answer for this, unfortunately, either. And there's even people are also more complicated. There's not a good definition for what material to use. So people use what's called the power figure of merit. But again, just like power density, there's different power figures that people use that basically say, okay, if you use an aluminum nitride, you might use one method saying that this is good for this, for aluminum nitride, but then PZT people might use a different one. So again, it's very difficult to determine what is the best material, and it depends on what application you're doing. So there's here I just show 4 different figures of merits. Again, they all have the piezoelectric coefficient, but this one takes it one step further. This has piezoelectric coefficient and the dielectric constant. This takes into account the Young's modulus and the electromechanical coupling coefficient, the density. So it really depends on what you define. And you can see this over here. So in this paper, they tried to review different piezoelectric materials and showing their energy harvesting figure of merits. Again, that was based on, that's why this is highlighted in red, because this is based on that term. But you see like your PZT, your zinc oxide, aluminum nitride, all within about the same, orders of magnitude anyways. But then, the nice thing with aluminum nitride is the recent, development of alloyed aluminum nitride or doped aluminum nitride, scandium aluminum nitride, which has potential to have much higher power density. But again, this still needs further research to be confirmed. But really, when you're selecting a material, you can't just go by just the power figure of merit. You got to look at other factors too. How easy is it to fabricate? Like the scandium aluminum nitride is not the easiest material to deposit. So you got to take that into consideration. Also, compatibility. So like some things, say PZT, for instance, if your other, say you have other electronics on your device that say CMOS that requires CMOS compatibility, well then PZT is probably not the best material because it's not CMOS compatible. So you got to take that in consideration. Also stress. Some of these have higher stress depending on how you deposit them. So you got to weigh all these things, and of course cost. If you're going to go to commercialization, you of course got to look at the cost of how the cost of the equipment, the cost of how to deposit this material. So you got to weigh all that stuff into your decision. Other things with power density are, other ways to solve power density is through piezo design. So again, this isn't true for all piezoelectric because, like, say, aluminum nitride and zinc oxide, they can only operate in this traditional D3-1 mode, which is given over here, where you have basically a capacitor structure. You have your piezoelectric material sandwiched between a top and bottom electrode. Well, as your beam bends, you're actually operating in this D3-1 mode, so it's stretching it or elongating the cantilever. But now, if you can, for ferroelectric materials, you can actually pull your piezoelectric material using interdigitated electrodes instead of this top and bottom electrode design. And then you can operate in what we call D3-3 mode, which usually D3-3 has a higher piezoelectric coefficient. So then you would therefore should be essentially a better energy harvester because you just have a higher piezoelectric coefficient than you do with D3-1. Other methods of design is creating a bimorph or stacked piezoelectric film. So this is also possible with ferroelectric materials such as PZT, but very difficult with like thin films such as zinc oxide or aluminum nitride. But so if you can control polarity and control the location of the neutral axis, this can be beneficial because then you have all of a sudden 2 layers, which then is essentially increasing your piezoelectric coefficient. But if you have a poor design of your bimorph, you could actually have a negative effect because you could have, one side would be under tensile stress and one would be under compressive stress. And then you could actually get a cancellation of your overall effect. So, you have to be careful of how you design this and control your polarity and your electrode design. Other methods to solve this are cantilever design. So you can have different structures of your cantilever. So here's a trapezoidal structure. Here's like a more rectangle, a skinny kind of elongated structure. So we've done a lot of finite element modeling and stuff to see like, okay, what's the optimal shapes and everything else to try to increase the stress at specific areas. People have also done colligated beams designs and stuff to try to maximize stress at certain points. This is one that we did, like I mentioned, the pacemaker. So we had to have this special proof mass design that looks like a sort of a bullet shape, and that was because we were putting our device in a capsule, a rounded capsule. So if we had this, like say, square or rectangle shape, the edges would prevent it from going the maximum displacement. So we had to try to round the edges and make this bullet shape so that way we increase our overall displacement and stress, which then increase the power. So going from power density, one of the next biggest problem that people look at is bandwidth challenge. So one of the most significant problems with micro energy harvesting devices is matching the resonant frequency with the frequency of the vibration source. So ideally, you want your cantilever and vibration source to be the same. And now for microscale devices, typically these are made out of silicon, which have very high Q factors or very narrow bandwidths. These bandwidths can be on the order of 1 to 3 hertz, or about 1 to 5% of the resonant frequency. So an ideal case, like I said, is where they match, but in reality, this almost never happens. And you have something like this, where your frequency spectrum is different than what your device, the resonant frequency of your device. And this can happen by a number of reasons. Your source might change frequency during operation. But also, even then, even if it doesn't, it's very difficult to design or manufacture your device to have exactly the resonant frequency that you want. Usually, even under the tightest manufacturing capabilities, you're still going to have about a 1 to 10% error. And this is due to various issues. When we do like finite element modeling of our cantilever devices, we assume perfect conditions, right? We have perfect edges, perfect, no surface roughness, no stress. You can add stress, so you can do that, but you don't add into account all this stuff. So in practicality, you have jagged edges, you have stress, you have again, even when you do your lithography, you're not going to have 90-degree sidewalls, you're going to have slants. All this stuff is going to add up and create some type of error. And even then, when you deposit say 500 nanometers in our model, say the thickness of your piezoelectric material is 500 nanometers, well, our model, we put 500 nanometers. In practicality terms, that's going to be off just even like 1%, 2% across the wafer just from uniformity. So, and if you have like 5 or 6 layers, all these, little differences in surface thicknesses of your thin films adds up and is going to cause problems and cause you to have, again, error in your frequency that you're estimating. So how do people solve this? So traditionally, the easiest way is to make an array of devices where you have basically different lengths, slightly different lengths. So then each one's going to operate at a slightly different frequency. And you're going to end up getting something that looks like this, where you have a bunch of different frequencies of all your different devices. And if you sum them up, you get something that looks like this, that basically widen the bandwidth. However, the problem with this is that you are really decreasing your power density because you're basically increasing your footprint. And also, then you also have to worry about interconnects because then you have to have rectifying circuits for each cantilever. So your circuitry is going to be a lot more complex. Other methods are increasing damping, which result in a low Q factor, something like this. But people have done this, like MIT. I think they were able to produce like low frequency devices that had like 200 hertz bandwidth, but then they only generated nanowatts of power, which is also, kind of limits your device. Yeah, and I already mentioned that power was a big issue, so we want to try to increase power. So we don't want to decrease the power. Other methods that people have tried are, nonlinear approaches. So people have tried putting repulsive or attractive forces, such as magnetics. People have tried duffing resonators, so that creates, nonlinear structures, something like this. But these have problems with, they have a sweep up. They have difference in hysteresis, such as if you sweep up or if you sweep down the frequency, which is not how practical devices actually work. They might just switch frequency, so then you fall somewhere in between. Then there's mechanical stoppers that people have tried. So these are putting like stoppers in, so like the tip of your cantilever stops and hits this, and you create nonlinear effects using this. But all these kind of work, but they're all limited in the amount of bandwidth that they can apply. So recently, people have tried to, in the last couple of years, people have tried to change the center of gravity. So if you can change the center of gravity of your cantilever, of your proof mass, you can essentially change the frequency. So, for instance, if you put if you change your center of gravity, say to the far end, you're going to reduce your frequency. If you put it more towards the tethered end, you're going to sort of increase your frequency compared to putting it in the center. So if you can create something that has like a sliding mass, you can essentially widen your bandwidth. And we've done this. So here I show a video of this. So we've done this we did this using liquid. So this is just colored liquid that we see. So we get a sloshing effect. And what we're really changing is the center of gravity as this cantilever oscillates. And we call this method dynamic tuning. And we were able to get, we were basically able to get a very high bandwidths using this and using different liquids. So this is just using water. We didn't get that much increase. But if we go into something that's more dense, like using liquid metal in here, we were able to get, a bandwidth increase from about 1.3 hertz to about 9 hertz without any significant decrease in power. Other methods of using a sliding mass include people have tried to use rolling masses or cylinders to do this concept. However, both this and the liquid have been shown at the macro scale, but at the micro scale, this gets very difficult because you're not going to be producing that much change in the center of gravity. You're talking about maybe changing the center of gravity by maybe 100 microns or so, which isn't going to increase your bandwidth very much. So we came up with another method that I just presented at a conference a couple weeks ago on, is instead of using a sliding mass, we have a vertical mass that we change. So essentially what we're doing is changing the effective mass or proof mass. So because like when it's down on the bottom, you're this sphere that we have, this movable mass, is contributing to the proof mass. But when we have it, when this is oscillating and the proof mass is, say, at the top, it's basically in free fall. So it's not basically accounting for any of the effective mass. And when we did this, we were just using, stainless steel spheres initially. We were able to get, significantly higher bandwidth, but at the cost of lowering the power. So it's always a trade-off between bandwidth and power. But we were able to get this is just 29 hertz, but we were even able to increase it up to 60 hertz bandwidth. So yeah, I'm gonna try to hurry up and finish. So frequency tuning is another method. So this is related to bandwidth. So instead of increasing the bandwidth, if we have our frequency here and our vibration source here, can we actually move our resonant frequency of our cantilever over to the vibration source? Something like that. So how do we do that? So if you look at the simple formula, we can't really change the width the thickness or the length during operation, right? You can't really do that. So you're left with either changing the mass, which can be done, but that's more difficult. Or another method that we can do is change the elastic modulus. So if we can change the elastic modulus, so we worked with people in Eindhoven who developed a smart material that basically changes it's a photoresponsive material that changes its Young's modulus based on light. So if we shine UV light on this material, it changes its Young's modulus, and that allowed us to change or tune the resonant frequency depending on how much light we put on it and what type of light. So if you use green light, blue light, or in what intensity, that changed the Young's modulus even more, and then we could tune it that way. So yeah, I only have a couple more slides. So reliability, I mentioned this early on. So this is not reliability in packaging is a huge issue and is often overlooked in academia because it's considered a sort of industrial problem. But this is one of the big challenges limiting these devices from going commercial, in my opinion. And really, so there's been a couple papers, mostly from IMEC and Belgium, who have been looking at this. But again, they looked at methods of packaging these devices, where to put certain areas to prevent stress or to prevent breakage, and also even looking at, again, different vacuums. So again, putting this under vacuum, obviously you're going to increase your Q factor, so you're going to increase your power versus having it in atmospheric pressure. Or in a open room environment. So this is a huge issue that I think needs to be looked at more in academia, anyways. I briefly mentioned application-specific design. So right now, every application requires a different frequency, a different acceleration, and this complicates things. Because what's the main advantage of MEMS? The main advantage of MEMS is batch fabrication capabilities, right? We can produce billions and billions of devices very cheaply. However, if every application requires a specific frequency and stuff, you take away that advantage. Then you might need to make say for if you're harvesting energy from a car engine, you would have to make a different energy harvester for every model of car, which that's not really price feasible. It's not really cost effective for MEMS. So this is a big challenge. So really what you want to do is, and that's why we're trying to increase the bandwidth, trying to tune these devices so that way we can make a more universal device that can work in many applications. So that way you can just fabricate one type of device and have it work in a wide range of applications. And that's sort of what we're trying to accomplish. Yeah, and there's different techniques of doing that, but I'm running short of time, so I would just talk about the summary. So in short, microscale energy harvesting is a critical component for Internet of Things and cyber physical systems. There are major challenges that still need to be overcome and applied, and hopefully some of you are working in this area and we come up with new techniques other than the ones that I had mentioned. And we can try to solve this problem, because we really need further innovation is required to get to commercialization. There's been a lot of research in this area for the last decade or so, and there's been significant advances in science and getting closer to innovation, but there's still no commercial MEMS kinetic energy harvesting devices that you can just buy that are commercial. And really, if you're working in this area, you got to think about not just the science, but also the industrial manufacturing, the practicality, and the end user. So with that, thank you, and I'll accept any questions now, or you can always contact me if you have other questions in the future. Thank you.
On behalf of this organizing, thank Professor Nathan for his current challenges in the field of piezoelectric energy harvesting devices. So whether we have any questions. So one question, it is asking that how to deal with the stress for getting a freestanding MEMS structure. How to resolve or how to deal with the stress? Yeah.
So how do you handle the stress? So yeah, the stress is a big issue because for energy harvesting, you want stress because that's how that's how it generates the energy harvesting, but yet you don't want to create so much stress to where it's going to break, where your device is going to break. So yeah, it's one of the big, like, what's the safety value? Like, yeah, you got a trade off. Yeah, you want high stress, but yet you don't want your device to break. So it's a big challenge, to overcome. And for the safety factor is usually, you don't want to go, a factor of 3 or so, above like what the fracture point is. But it's something that you always need to look at. And looking at the accelerated testing for these is difficult to do. So yeah, it's quite a challenge. Yeah.
We have another question is Nadeem is asking how to quality aluminum nitride piezo film for vibration energy harvesting.
Yeah. So how do you deposit good? Yeah. So depositing aluminum nitride is rather difficult. I spent when I was in Ireland working in a national lab there. I spent about 3 years perfecting our aluminum nitride process. So it took time to do it. It's one of those materials. It's easy to deposit an okay material, but it can be very difficult to deposit a very high quality material. Because it depends on all the different, we were doing sputtering, but it depends on all the different parameters. It also depends on, what system you have, what underlying materials you have. Yeah. Temperature, pressure, all that stuff. So there's a lot of different variables, and you got to just, try to perfect it the best you can. And then when you get into the alloyed aluminum nitride, then it's even more complicated. If you're trying to go with the scandium aluminum nitride, like I said, there's huge benefits in that, but people have been working on trying to deposit scandium aluminum nitride for 10 years now. And they're improving it. It's getting better, but it's still quite a challenge. So, but yeah.
We have many questions, but because of time limitation, I will stop it now, and I will try to send all those questions to you, and hopefully these participants will also write email to you. Okay. So let's thank once again Professor Nathan for this wonderful talk. Okay. Now I like to welcome the second invited speaker. So just a minute. So she is Dr. Shohini Kar Narayan. So Dr. Shohini is an assistant professor at University of Cambridge since 2018. Earlier, she was a university lecturer in the same department since 2015. Dr. Shohini has received BSc Honors in Physics in 2001 from University of Calcutta, India. Okay, she has done her PhD in Physics from ISC Bangalore. And after that, she has worked as a postdoctoral department at Department of Material Science in Cambridge. She was awarded a prestigious Royal Society Hodgkin Fellowship in 2012. Okay, so Professor Shohini is a recipient of World Economics Forum Young Scientist Award. Okay, so let's welcome Professor Shohini, and she is going to talk about her research in this quick area. Okay, so Professor Shohini, you can begin now. Okay, we have some internet issues, seems, so I'm going to stop my video. Okay. You are muted. Professor Shohini, yeah. Professor Shohini, you can unmute yourself. Yeah.
Hi, can you hear me?
Yes, now we can hear you clearly.
All right, sorry about that. I wasn't able to find the unmute button. Can you see my screen?
Yes, certainly.
Okay, I'll try to go into slideshow. Okay, that's good. Okay, great. So good. I guess it's good afternoon for everyone in India. So good afternoon. It's actually early in the morning. Well, about 8:30 in the morning here. So good morning or good afternoon or wherever you are. And thank you very much for this invitation. So I'd like to thank the organizers for inviting me to this conference. And today I'm going to be talking about rapid prototyping of microfluidic devices with versatile geometries and functionalities. Now, as I've been kindly introduced, I work in the University of Material Science at the University of Cambridge, Department of Material Science. Sorry. And my work actually spans quite a few different fields. Now, since this conference was sort of about MEMS devices and microfluidic devices as well, I decided for this particular talk I would talk about some of our very recent work on microfluidic devices. But for those of you, for many of you who probably don't know me, I just thought I'd start by giving you a sort of overview of my group. So. So it was actually very interesting listening to the previous talk on sort of piezoelectric systems. So a lot of our work is actually based around energy harvesting. So our original work that my group works on is based on energy harvesting. And sorry, I don't know why this thing's sort of moving on its own. But anyway, so we do a lot of work on mechanical energy harvesting systems and thermal energy harvesting systems, as you can see on this slide. In terms of mechanical energy harvesting, we've been working on piezoelectric materials, but we've been looking at mostly polymer-based piezoelectric materials, so organic materials. And the reason we look at organic materials is for some of the issues that were raised previously, which include the fact that these materials, the traditional piezoelectric materials are often stiff. There are issues with applying high stresses or high strains to them without causing failure or mechanical other mechanical issues. And so we've been looking at polymer-based piezoelectric materials for mechanical energy harvesting. I'm sorry, my sorry, just one second. Hang on, sorry. The PowerPoint seems to be moving on its own. Apologies for that. So sorry, coming back to what I was just mentioning here, the type of materials that we work with are often polymer-based because we are trying to overcome limitations with respect to their mechanical properties. And in particular, because polymer-based piezoelectrics are not as high performing as, say, ceramic piezoelectrics that you may be more familiar with, say PZT, etc. What we would do is we actually work at the nanoscale. So by working with nanostructured polymers, we can actually enhance a lot of these properties and therefore make mechanical energy harvesters. So in the top left figure here, in fact, one of the other advantages of working with polymers is that you can make flexible devices, stretchable devices, and you have a lot more there are quite a lot of geometries that you can access easily, which may not be easy to do with, say, traditional ceramics. But today I'm not actually going to be talking about that. In fact, I won't even be talking about some of the other interesting things that happen in my group. For instance, we work on thermal energy harvesters. So again, same thing, we're trying to look at ways by which we can bring organic materials into this field so that we can increase the sort of range of devices. So we can make, for instance, in this figure here, we can make these very nice flexible devices which can be used for, again, wearables, IoTs, where rigidity might be an issue. And then we have, of course, the way we go from materials to devices, sorry, is using various additive manufacturing techniques. So with these, we can make flexible and stretchable electronics. And these advanced additive manufacturing techniques essentially involve some sort of printing. But these may be different printing techniques to what you may have come across previously, such as aerosol jet print, such as inkjet printing. And this I will discuss actually today in a bit more detail. On the subject of functionality, we are interested in looking at piezoelectric properties and materials in other settings. So for instance, we do quite a lot of work with piezoelectricity in biological systems. And the reason for this is a lot of our devices do actually end up in biomedical devices. And so we have quite a bit of work going on in the biomedical sensor area. And so this sort of brings me to what I want to talk about today, which is microfluidic devices. Now, this seemingly seems a little disparate from everything else that I've been talking about, but as you'll see, a lot of the materials and methods that we have, we work with normally, the idea is to bring these to this sort of microfluidic platform, so that instead of having just channels which can direct fluid, these channels can actually be active. They can be functionalized. So I'll talk about mainly this aspect of my research today. And I just wanted to touch on the fact that we do a lot of scanning probe microscopy, because we work with a lot of nanomaterials, and as you know, nanoscale properties differ significantly from bulk properties. And so it's important to be able to characterize these properties at the nanoscale for these types of different materials. So this is just sort of a snapshot of all the different kind of aspects, all the different research directions that my group takes. So this brings me, wonderful, there we go. So this brings me to what I would like to discuss today. So I mainly want to talk about microfluidic devices and sensors. This is actually quite a new research direction in my group, so I'm actually quite excited to be talking about this. This is, I think, the first talk that I'm giving about this aspect of the research. And there were so microfluidic devices to me have always seemed like a passive platform. So you make these these tiny channels which allow high throughput experiments. You can guide fluids where you want to. You can use them, and they are used for in a lot of biological settings for range of different sensing applications. But the channels themselves are, if you think about it, they're just there to guide fluid flow, right? Or to make sure that if you start off with a small fluid volume, then you're able to split this up and direct fluid on this platform. But the channels in that sense, at least to me, are passive, right? They're not really taking part in any application as such. And so my idea, because we work with a lot of functional materials, is can we functionalize the channels themselves so that they become active, so that they can actually partake in whatever reaction or whatever sensing application that they're being employed for. The other issue is, of course, how do we read off these microfluidic devices? So typically, microfluidic devices are meant to be very small. You can move them around very easily. But the fact of the matter remains that in order to actually analyze these devices, you still need, often you need these huge microscopes, and you need labeled molecules which maybe fluoresce, etc., so that you can actually see what is going on. So there's still a centralized system of trying to analyze what is going on in a lot of these microfluidic type devices. So one of the ideas we had was to really make it point of care, to really make these standalone devices such that you do not require the microscopes. You can actually maybe take a sample and do the analysis right there without needing any more specialized equipment. So the way to do this would be, again, coming back to introducing more functionality into these microfluidic devices, so that we can actually read off signals without requiring optical cues, which is typically what these devices tend to require. So so for that, we need a few things to work. One is, if we make these devices in the sort of the traditional way that they're made, then it's actually hard to include further functionality. So what we came up with was a new rapid prototyping method that can manufacture microfluidic devices, which I'll tell you in a bit about. And this technique allows us to change the design very rapidly, but it also allows us to reach geometries which would otherwise have been very difficult to do. So that was the first thing, to prove that this method can actually be used for the first time to make these microfluidic devices. And then to optimize the microchannels, so to test for the fact that fluid can flow, the fact that we can change dimensions easily, the fact that we can introduce, as I mentioned, other elements into these platforms. So that brings me to probably the most important bit, which is to improve the functionality. So to introduce functional materials into the channels, or to integrate with electrical circuitry. So the reason why this last bit is particularly important is because if you can integrate electrical circuitry into these platforms, then it means that not only can you sense electrically, so you could in principle connect this up to your laptop or your mobile phone and read off electrical signals to find out what's going on, but also it gives you the ability to control what is going on, because you can apply signals and cause reactions to occur or something else. So how do we manage? So how do we basically make our microfluidic devices smarter? And remember, when I say improve functionality, it can be any type of functional material. So we've been listening to talk about piezoelectric materials. Would it be possible to introduce piezoelectric materials into these channels, such that, for instance, you can induce mixing or a graded flow within these channels without requiring, say, the pumps and all of the paraphernalia that go around these microfluidic labs. So the way that we the way that we wanted to do this was using a method called aerosol jet printing, which I will talk about in a bit more detail, but suffice it to say that it is a direct write printing method. I think it's closest, the closest I can think of is probably inkjet printing, but it is a very, very different mechanism. And one of the main advantages that aerosol jet printing has is that it can handle a variety of different inks, which say inkjet printing would not necessarily be able to do. So, for instance, the viscosity of the ink is often a big issue for any direct write technique. Whereas for aerosol jet printing, I joke about this, but you can basically print anything between milk and honey. So the viscosity of the ink is not really an issue. But the most important thing, I think, is that it gives you very fine resolution. So you can go down to feature sizes of 10 microns, and you can print over large areas. So you can get both the small resolution as well as the fact that you can do this over a large area. And that resolution is important because 10 microns is typically what you would get using, say, photolithography, which, as if any of you have ever done this, it's it's quite a cumbersome process, not the most easy to scale up, and also if you're trying to combine different materials, it becomes hard. So this is a problem with microfluidics. In fact, the fact that at least for most research grade devices, these are usually made using a method that depends on photolithography. So the way it's done, so these are the steps typically, is you have a substrate, you coat it with a photoresist, and then you use some UV radiation to mark out a pattern. So this, essentially what you're trying to do is you're trying to create a mask. And once you've created that mask, you then cure the photoresist such that when you wash that mask off, the bit that you've cured still remains on the substrate, as you can see. And this is what is called a mold. So now if I pour on, say, PDMS or some other a polymer, and I allow it to set on this cured photoresist, then I can peel this polymer off, and then you're left with the microfluidic channel. So this is typically how it's done. It works, and you can get good resolution. You can make complex patterns, but it's as I said, if you've ever done photolithography, it's not the easiest method to work with. Once you have this mask, if you had to go back and change it, you'd have to start this process all over again, which is quite painful. And there are limitations as to what kind of geometries you can achieve with this. And again, for those working with photolithography, you'd be more aware of some of these. And these are the kind of things that we wanted to overcome. And also, if we wanted to introduce more materials into the channel, it's in this particular system, or in this particular process, it becomes quite difficult. So this brings me to there we go. So this brings me to aerosol jet printing. Let me just tell you a little bit more about this method, because we use this extensively in my lab. As I said, not just for microfluidic devices. In fact, originally it was to make these functional energy harvesting type devices, where we would make polymeric inks or nanoparticle based inks, put it into this aerosol jet printer, and then start to make devices out of it. So you can not only print as I mentioned, functional materials, where you can of course print all the interconnects, all the the layers of encapsulation. Again, we heard how important encapsulation is. So you can really build up an entire device by printing sort of layer by layer these different materials. We have a lot of papers out there which describe this method in great detail. But the main idea is that you have you essentially have an ink which you can create an aerosol out of using either what is called an ultrasonic atomizer or a pneumatic atomizer. So basically, you create really tiny droplets out of the ink, and then the ink is jetted out. It's basically these aerosols, rather, these droplets are picked up with some nitrogen gas and then sort of jetted out via this nozzle. Let me see if I can get my a pointer. Oh, here we are. I think that'll be easier. There we go. So yeah, so we load the ink into a chamber and or an atomizer, and then the ink is atomized, and then you have a nitrogen gas which picks up this ink and jets it out of this nozzle. As you can see, and here's a video sort of showing you this thing at work. And as you can imagine, when you jet something out of a nozzle, you'd expect it to kind of go everywhere. And it does. So we have a second sheath nitrogen gas line, which sort of focuses this jet, and it focuses it down to a very narrow drop size, if you will. And this is basically what is directly written. So you can see actually this pattern being formed here. Oops. You can see this pattern being formed right here. So the advantage of this, as I mentioned, is that you have a variety of inks that you can deposit in this way. You can get down to feature sizes of 10 microns, and the most important thing is you can just keep changing the ink, and you can grow things layer by layer. So you can put in fiducial markers, so you can go back to the same place. It's quite a versatile technique, and you can do this on a variety of different substrates, rigid, flexible, what have you. And so, yeah, if you're interested in this and how we've used this for, so in fact, some of these papers here describe thermal energy harvesters that we've made using this method. So, please do look at these papers. So how do we use this for microfluidic devices? Well, what we do is we directly print out the mold, right? So we directly print out the mold from which you would create the microfluidic device. So here's what this setup looks like. This is a lab-based setup, but then they do have industrial size aerosol jet printers, which is good news because it means that whatever you do on the lab bench can be translated to sort of large scale production. And you can kind of see this is where our deposition head is. All the rest of the, these are sort of the atomizers where your ink will go, but all the action takes place down here on this platen. So the nozzle stays fixed while the platen moves around. So you load up your design and then set the printing going, and then the platen will take care of the rest. So here's the schematic of how we do this. So like I said, you print your deposit onto a substrate, and then you can pour, for instance, PDMS or any other polymer. It doesn't have to be PDMS, although PDMS is the material of choice for microfluidic devices. And then when you peel this off, then your PDMS is left with the channel, and you can kind of bind this to glass or to any other substrate, and that essentially is your microfluidic channel. So why is this better than photolithography? Well, for one, it's basically a one-step process because it's direct writing. There is no photoresist and making a mask and all alignment and all of that. You literally just you have your design. You can make up a CAD file, and then you go in and you print it. But because you print this layer by layer, you can control the size of your microfluidic channel. So you can go from really thin to really thick just by building up the layers. So the other nice thing is that you can change the geometry of the layers as you go by. So you don't have to have just semicircular channels. So this is sort of looking at the channel kind of head on. You can have these semicircular channels. You can have these triangular channels. You can have rectangular channels. The geometry becomes so much more easier. This is almost impossible to achieve using photolithography. So that's great, the fact that we can go to all the, we can have these varied mold geometries. What else can we do? Well, we did just a few standard tests to show that, the quality of the microfluidic channels is the same as you would get from a photolithography type device. So here's a gradient generator, basically. So we printed out this complex pattern here. So essentially you jet into different inks, and as they go through this gradient generator, you end up at the bottom side here with this gradient in either intensity or color of the inks as they mix at each of these stages. And so, these are just demonstrations to show that, it works. It doesn't affect the flow or any other aspect of the microfluidic channel. All of these results have been published in a paper that came out earlier today that describes this method a paper that came out earlier this year in Applied Materials Today, where all of these are described in great detail. This we found particularly exciting, the fact that you could not just change the shape of the channel, but you could also change the morphology of the channel. So, for instance, you can vary the channel height. So rather than having just sort of uniform channels, which is what most microfluidic devices have, you can have slopes or steps. And so you can see how we do that. So here's you can see the molds that we create. So this is actually the printer nozzle that is jetting out these molds, as you can see here. And you can see that we can create different step patterns or different slope patterns. And all you need to do is to vary the number of layers that you are printing for each pass. As I mentioned, this is almost impossible to do by photolithography, but there are lots of applications. So we work very closely with cell biologists and people in the biophysics sort of side of things. And they find these kind of structures or these kind of channels where you can actually vary the height or the slope very useful for quite a few of their experiments. So this brings me to functionalization. So at the start, I told you that our main goal was to introduce other materials into the channel, functional materials into the channel that could do something, right? So here's an example of a passive functional material. And when I mean passive, all it means is that it's functional, it has a purpose, but once we put it in there, we don't control it from the outside. So an active functionalization would be, say, a piezoelectric element, where you could actually control what the piezoelectric element is doing from the outside. But for proof of concept, we just wanted to show how you could actually get a material in. And it's quite easy to do with this aerosol jet printer because, okay, here we go. We first of all, we print our mold. So this is what we would do for our channel anyway. And then we print the functional material on top of that mold. So this is a coating of whatever functional material you want to put in that we use the aerosol jet printer to jet on. And then we carry out the steps as before. So we coat the mold with the functional additive using PDMS or any other polymer. And when you peel this off, it actually takes off the functional material or the functional coating with it. So that when you then stick it onto your glass or your cover slip, you end up with a coated channel. So this is a microfluidic channel, which now actually has a functional material within it. So let's explore an application. So one of the first coatings that we tried was a material called PVA, polyvinyl alcohol, which I don't know if you've come across before, but it's a hydrophilic material. And what we had done was we made this sort of a channel, so a T-junction, where on one side of the T-junction we had PVA coating, and on the other side we had no coating. This is our sort of control layer. And when you introduce fluid, when you introduce a liquid through the inlet, because the PVA is hydrophilic, it draws the liquid towards itself because it has an affinity to the liquid, and you can see how it flows down this particular channel, but not so much the channel with no coating. So this is very exciting because this is an example of a functional microfluidic device, right? Because the channel is partaking in how this fluid is split up, how this fluid is flowing through the channels or through the device. And we did this using this very well, to us it's quite a simple technique. But the important thing is we can scale this up quite easily. And so these types of devices, as I said, have lots of applications because PVA is not, of course, the only material that we can coat this with. We can coat it with all sorts of biological material or other chemicals or reagents that might be of interest, so that you can have reactions happening at specific points within your channel as you would wish. So it does introduce a lot of as I said, not just functionality but control for the users as to what your device ends up doing. So aerosol jet printing allows you not just to do sort of two-dimensional printing as you would have with inkjet printers, but instead you can actually grow these lovely three-dimensional structures. So here we are actually printing wax. This is a kind of designer wax that people use for for jewelry, and we show that we can do this using the aerosol jet printer, which is quite nice because you can really build up these structures. So here are some 3D microfluidic molds. All microfluidic devices operate in 2 dimensions typically. But it's sort of like the difference between living in a bungalow and living in a skyscraper. You know, if you can build up in the 3rd dimension, then you have more room to have these reactions or what have you, whereas you keep the footprint area still the same. So it's an interesting concept. You know, what happens if I actually go into the 3rd dimension? Can I can I have more flow reactions? Can I increase the area over reactions over which reactions can occur, but maintaining the same footprint area? So here are some examples of 3D microfluidic devices. So, you know, we print our wax. That's what it actually looks like. It has a greenish color. You cast your PDMS. This is sort of looking at it from the side. You can see the wax sitting in there. We have some inlet and outlet holes. And the reason for this is, you know, we need to get rid of the wax to make the 3D channels. And the way we do this is by passing, you know, a chemical or a reagent that can dissolve the wax away, and then we extract the wax. So then you're left with these beautiful 3-dimensional channels in PDMS, and you can, you know, make up these devices. So the gradient generator, for example, that I showed you, which takes up quite a bit of area on a 2-dimensional piece, you can you know, sort of like I said, you know, make a skyscraper out of it and have it operating in a much smaller region. So you can do all these really fun stuff. But what I wanted to highlight is how you can start to make really interesting sensors out of these, you know, by combining different functionalities. So here is an example of an aerosol jet printed conformable microfluidic sensor. So far the microfluidic devices that I showed you were on glass, which is rigid. But you can replace the glass. So here we use a Kapton substrate. This is polyimide, which is nice and flexible. And what we've done is, you know, here's your channel. And what we've done is we've underlaid this with some interdigitated electrodes, which you can see at the bottom here. So the idea is, as you apply force, it forces the liquid up the channel, and as it flows across these electrodes, it changes the local the dielectric constant within the channel, and you can sense this externally as a change in capacitance of these channels. So, and then if you can calibrate that, so as a function of force, the higher the force, the more the fluid will flow, and so the larger the change in capacitance, and then you have a very nice force sensor, which, you know, can be very small, as you can see in the pictures below here, very thin, and indeed very compliant and very conformable. So, here's a video of this one. Let's see this plays. So yeah, if you look at this, this is essentially what's happening when you apply a force. The liquid moves across the channel, and because we have those electrical connections within there, because we have those interdigitated electrodes, we sense what is going on, like how much liquid is flowing, and hence how much force is being applied. Okay, so this particular one actually is made in a very interesting way. So the mold material that we use is actually, so the way we create the channel is actually by printing salt. And when I say salt, I mean table salt. So we make a really concentrated solution of NaCl, and then we print out this mold. And then, you know, you put down your once you have the mold, you put down your PDMS. We print this on a foil, which you can then peel off, as you can see here in figure C. So, sorry, let me just find that pointer again. Yeah. So we peel off the back side, and you're left with this mold with the salt. And because it's salt, you can dissolve it in water. So we just stick this in water for a while. The salt comes off, and you're left with a nice microfluidic channel. Separately, we print out our electrodes, and this is using a silver nanoparticulate ink on a polyimide substrate. And then you bring these two together. So you stick one on top of the other, you overlay it, and that's it. And that's your device. You fill it up with fluid just to fill up the reservoir, and this is the fluid which will eventually move up and down. There is another step in this process. So after we do the electrodes, we also put down a thin insulating layer so that the liquid is never in direct contact with the electrodes, as it can interfere with the operation. So here's some images of what it looks like. So like I said, we do print salt. So here's a top view of a salt mold, as it were. Here's some nice SAIN images showing you what these look like. So if the number of loops, you know, if you print more layers, you can increase the thickness of your mold. This is the central reservoir region. We make it in this pillar form just to give it a bit more stability. And yeah, so here's our device at the bottom. And the way we test this is we have a force. We have a mechanical motor system which can apply forces at particular values, and then we can measure. So you can see the wires which go to an impedance analyzer, and you can measure what changes in capacitance there are. So okay, here we go. We've done a lot of this calibration. So the first thing that you see is that if you look at the capacitance as a function of force, it's nice and linear up to a certain value. We back this up using finite element models to see, does that match up? And it does, which is great. And you might wonder, well, it starts to flatten out here. Well, it does so because essentially what happens at this point is that the liquid has reached the end of the electrode. So any further force just doesn't create any further changes. So what we can do is we can change the geometry of the channel. And as I said at the very beginning, this is very, very easy for us to do using this method. So all these graphs that you see here, I won't go into them in great detail, but they're essentially changing various aspects of the geometry of the channel. So for instance, you can change the length of the channel, the height of the channel, how long your electrodes are, how stiff the material is, right? So if you have a stiffer, material, then you'd have to apply more force to get the fluid to move. And all of this has an effect on the sensitivity and the range of forces that you can apply. Which is great because this method allows you to design your microfluidic sensor to suit the particular force that you want to measure. So if you want to measure really small forces, then you can make it super sensitive by picking the right set of parameters. If you want to make it go to high forces, then you pick the right materials, the right geometry, so it will allow you to go to, instead of 8 newtons in this case, you can go up to 100 newtons even, as I'll show you in a minute. Now, all of this, if you're interested in looking at, you'll be able to find in this preprint, which has actually recently been put out there, where all of this is described in great detail. So not just the how we make them, but also all the results. So I just wanted to end with one very quick, a nice example of how these force sensors can be used in an actual application. So we've been working with an orthopedic surgeon to show that you can use these sensors during orthopedic surgery or for telemetry. And the reason for this is, so the surgeon we work with is a hip surgeon who conducts hip replacements. And the way they do this, when they insert the sort of the artificial hip or the hip implant is, they take out the bone and all of that. But when they go to fit this joint, it's done by feel. So they have some anatomical markers for sure, but then it depends a lot on the surgeon's skill, how well they can fit this, fit back the hip. And if they don't get it right, then you need joint replacements. In the UK alone, for instance, we have like 250,000 joint replacements that are needed. And this becomes a bigger problem because apparently there are younger people who are needing hip replacement surgeries now. And so the quality of life starts to diminish if they need to come back every few years to have their, implants replaced. So the way the way to make this process more accurate is if you actually have sensors, right, that can guide you, that can help with the balancing of this hip. The problem is if you look at that joint, it's a very tight joint. How do we get force sensors within such a tight joint? And also it's a weird shape. So, we need a conformable force sensor that can measure these large forces. And that's exactly what we've been working on, right? Like I said, we're making these force sensors, which we can change the geometry or the material quite easily in order for them to be able to go to higher and higher forces. So let's see if I can get this video to play. So these are our force sensors that I showed you. And the idea is to stick this into what's called the acetabular cup, which is part of the implant that goes into the hip joint. So having the sensors embedded in this way means that, because it's conformable, it can take the shape of that hip joint. Because they're thin, they can easily fit into the cup without making any substantial changes to the implant. And you can now get actual, real force measurements. Sorry. So this is what it looks like. So these are sort of the components. Let me just find my. So these are the different components. So these are the inserts which would normally go in. This is the sensing cup. So this is where we load our sensors, and this is called the femoral head. So this is the other part of the hip joint, which when the surgeon is sort of adjusting it, trying to get the right positioning, they can actually read off the forces from these sensors in order to guide them to do this, which is great. Just a quick video to show you This is just a tabletop version of this, how it works. So we made like a simple software to go with this. So you can see as the forces are being applied, you can see how the force distribution is in this array of sensors. And mind you, what we're showing here, the cup is 3D printed, but the femoral is an actual implant head that is used, that the surgeon gave to us. So just to show you that again, you can really read off these forces of the various sensors. Okay, so I think I'm almost at the, oops. Oh, sorry. I exited. We are at we just got some funding to do some cadaveric testing. So we are actually going to try this in actual hip joints to see how it works. But in the meantime, we've got these sort of mechanical testing units within the lab that we've grown. So this is using a really like a hydraulic mechanical tester where we can mount our joint. So you can see that's the joint with the different sensors connected to the impedance analyzer. And we can apply different forces using this mechanical tester in order to see how the forces are distributed. Sorry, I think I'm out of time, so I won't go into great detail. But just to say that we can check these equations to see what these force distributions look like. So that brings me to the end of my talk. Apologies if I've overrun a bit. But yes, just wanted to acknowledge my fantastic group who do all the work. Everything I discussed today was done by a student called Liam Ives, a postdoc called Chin Sheng Jing, and Norden Tatik. So if you have any questions, I'd be happy to take them. Hello?
Yes. Can you hear? Yes.
Yep, I can hear you.
Yeah, I really like to thank you for this presentation. Very nice.
Thank you. I'm just trying to exit this.
Yes. So due to time constraints, let's. I will ask this organizer to send you all the questions from the participants.
Sure. Thank you very much.
Yeah. Thank you. Yes. Yes. Sushil, can you hear me now?
Yes, sir.
Okay. Yeah. So now we have the third presentation. I believe that this is a recorded version, right?
Right, sir. Now I'm requesting to host team to please run the video, please.
Yeah. Yes.
Hello everyone. In the course of next few minutes, I'm Shruti Patil from Department of Electrical Engineering, IIT Delhi, is going to present the topic Designing mass spectrometry. The development of chemical analyzers has been of great interest for the identification of composition of samples. Mass spectrometry is a gold in the field of material analysis. Major applications of this technique include motion control, healthcare, space exploration, food control, detection of process, etc. These applications require mass spectrometer to be small, light, robust, and lightweight. Miniaturization addresses most of these requirements. It helps in achieving portability of instrument by reducing the size and weight. Of the many varieties of mass spectrometers, quadrupole mass spectrometers are the ones which can be operated at higher pressures. The resolution of quadrupole mass spectrometer or QMS increases with increasing length of the rod. As we know, MEM scale QMS will have limited resolution due to their small length. Here are some MEMS based QMS. So we are presenting 3D printed QMS which promise a better balance between resolution and higher pressure operation. Also, 3D printing gives better alignment of different components. So now we will start with the basic introduction of mass spectrometry. The chemical species are ionized and sorted on the basis of mass to charge ratio. Here is the block diagram of a mass spectrometer, which consists of an ionizer, a mass analyzer, detector, and a vacuum chamber. The ionizer is used to ionize the sample, mass analyzer to filter the ions, and detector is used to detect the ions. Also, the whole setup is placed in a vacuum chamber. Here is the design of our QMS. You can see we have used hollow cathode as ionization source. After ionization of sample in the ionization chamber, the ions are accelerated with the help of accelerator and then goes to the pole mass filter where ion having a particular N by Z is passed and reaches to the detector. The detector count, if plotted, generates a mass spectrum, which is a 2D representation of the ion abundance versus M by Z. This provides the relative quantities of each M by Z within the sample. So now the first step is to ionize the sample. For this, there are several ionization techniques such as electron impact ionization, chemical ionization, field ionization, etc. For a sample consisting of a complex spectrum, soft ionization is preferred as it is easier to interpret it. We have used chemical ionization, which produces less fragmentation. In our work, we have used air as a carrier gas. As I mentioned earlier, ionization source used is hollow cathode. From this figure, you can see ionizer slots where we have placed two brass plates with a hole of 1 mm diameter. The gap between the hollow cathode needs to be designed according to the operating pressure of the device. The parallel plates are used for the breakdown of air is supplied via capillary, as you can see from this figure. Now, ions producing during breakdown of carrier gas then goes to the ionization chamber. Here you can see another capillary is used for sample inlet. Sample from this inlet goes to the ionization chamber where it ionizes by using air plasma ions. Moreover, the QMS system works with a certain minimum initial energy. For this, accelerator is used. Accelerator slots are shown in this figure. So now let's move to the next component of QMS, which is quadrupole mass filter. A QMF consists of 4 electrodes on which we apply a combination of DC and AC voltage. Let's consider red electrodes in X direction with plus phi naught by 2 potential and blue electrodes in Y direction with minus phi naught by 2 potential. For most quadrupole applications, omega is typically of RF range. Therefore, AC can be referred as RF. The ions are accelerated in Z direction. So, by traveling, they oscillate in XY plane due to the potentials applied to the rods. Within the quadrupole, an ion experiences no force in Z direction. So now to understand the motion of ions, Matthews stability diagram is used, which is shown here. Assume singly charged positive ions case. So if we fix frequency and mass of ions, this type of plot can be obtained by varying U and V. For the stability of ions, the ion trajectory should be stable in both X and Y. If we fix U, the diagram can be analyzed very easily. From this figure, you can see points C and D correspond to stable trajectories. From the next figure, you can see that both X and Y are stable at these points. Now at point A, RF is switched off. Now the rods which are along x-axis will repel the positive ion, which causes them to oscillate in x direction. Rods along y will attract the ions, causing the instability. Now, as we move from A to B, RF is increasing, but it is still low. So Y is still unstable here. At point C, Y portion becomes stable along with X. Moving from C to D and then to E, the AC is still increasing, but now its action is destabilizing, as high AC voltage causes ions to ultimately strike the rod. So now how quadrupole acts as a filter? To answer this question, consider a generalized stability diagram using the values of A and Q, which applies to all M by C. Now the line along constant A by Q is called as mass scan line. Mass spectrum can be generated if the DC and RF are scanned at a fixed ratio of A by Q and the number of transmitted ions are recorded as a function of M by Z. So now if we operate our QMF at the apex of this stability diagram, that is at point B, only ions of specific M by Z will have stable trajectories, hence filtration can be done. Here you can see the 3D printed QMF where slots of rods have been made. 15 mm SS rods are used for quadrupole. The moving ions from the QMF strikes the detector. We have used Faraday cup as detector. Here you can see Faraday cup is constructed as a cylindrical cup which is coaxially enclosed within a grounded outer shell. We have designed Faraday cup using brass cylinders. These cylinders are separated by ABS material. In the figure, you can see these alignment marks for aligning the detector with QMS and ionizer. This figure shows the entire QMS system with all components with proper alignment. Now coming to the results, we have simulated QMS using COMSOL multiphysics for chemical surrogates of sarin gas, TNT and mustard gas. The table given here gives the base peak of these surrogates. The Matthews stability diagram is plotted for these surrogates. For the testing of the device, we have operated it at 5 millibar pressure. Air is initially ionized, which mostly comprises of nitrogen. Blow discharge is created using hollow cathodes at 420 volts. The accelerator is operated at 320 volts. Current of 12 microampere after ionization of air is obtained. Then we inserted the vapors of ethanol through capillary. Here we obtained 44 microampere current without QMF. This shows that ethanol is ionized. For the testing of whole device of QMS, we applied 1.65 volt DC and 10.3 volt RF at 2 MHz, which is a stable point for nitrogen ions. The current obtained is the when QMS is off and 22 microamps when it is on. This shows QMS is working properly. So in the conclusion, I would like to say that we have simulated QMS using COMSOL multiphysics. Then we developed a 3D printed QMS in which we incorporated alignment marks and tested it for nitrogen ions. The 3D printed system is very light in weight and of low cost. Moreover, in future, we would like to test our QMS with more M by Z so as to get a better system. In the last, I would like to acknowledge Central Research Facility of IIT Delhi and MHRD for fellowship. Thank you.
Okay, thank you, Shruti, for your presentation. Now, Shruti is here. If you have any questions, you can direct those questions to Shruti. If there are any questions from the audience. If there are no questions, let's thank Shruti for her presentation. Okay, now we are going to have the last presentation from Shumit Saha, who is a PhD student in IIT Bombay. So Shumit, can you please start? And all the audience, I have to leave very soon for another department meeting. So Professor Pushprat Singh will take over as a role of the session chair.
Okay, so thank you. This is Professor. This is for be here. Yeah, I'm here as a essential now. Thank you.
Hello.
Yes, Sumit. Please go ahead.
Yes, sir. So sir, my screen is visible, na?
Yes.
Okay. Thank you, sir. Thank you. So okay. So sir, can we start now?
Yes, please start. Yeah.
Okay. So good afternoon, everyone. So I'm Shumit Shah. I'm the PhD student of Indian Institute of Technology, Bombay. So my presentation topic is fabrication of CMOS compatible two-terminal names for low-power electronic applications. So I'll briefly tell about the motivation of this working principle of the names also. And preliminarily, I'll show the fabrication and characterization of the two-terminal names. And subsequently, that is the primary device what we have fabricated, and then followed by three-terminal and as well as four-terminal names also we have fabricated. So I'll show these things, and then I'll conclude and reference and followed by the acknowledgements. So the motivation of this work is basically, so as we scale down the CMOS technology, so we know that the leakage and subthreshold slope. So these are the two barriers actually for scaling down. So that is if you see the figure A, so means the dynamic means the leakage energy is much higher as compared to the dynamic ones as we scale down the technology. So that is the limitation of the CMOS technology in terms of energy efficiency. And as well as means people are now people came up with the parallel cores. That technology also means multiple cores. But if each core operating at minimum energy, so as a whole, it will give that much of leakage energy as well. So the leakage energy is the primary barrier for scaling down. So that's why we are looking for some better switches which will give the essentially zero leakage perspective as well as the almost zero subthreshold slope. So if you see that the names is one of the promising candidate for this, if we replace this CMOS technology with the names technology. So as we see that that is, I'll show the what is the working principle, and this is the means the working or the looking like means the two electrodes are given, and between two electrodes air gap is there. So I'll show quickly go through the basics of names. As we know that this is the means primary structure of the names. So two electrodes are there, and it is basically electrostatically actuated device. So if we apply the voltage in between two electrode, and then if the electrostatic force is much more than the spring force, then it will come down and touches with the bottom electrode. So then only the conduction path will be formed. So that corresponding voltage is called the pulling voltage. And when means if we reduce the voltage, then it will come back to the initial position. So that means corresponding voltage is called pull-out voltage. As you see in the figure C, and that is a ideal names characteristic. So if you see that based on this characteristic, we can go for the names technology. So it will give the offset leakage zero kind of due to its air gap, and then steeper subthreshold slope. So we have done some names work. So our work approach is basically we have simulated the names with proper specification, and then followed by that we have calibrated the simulation results with a theoretical value, means these equations and then this force balance equation also. And then finally we go to the fabrication in our SAIN lab, and then validate the measurement characteristic with the simulated ones. So I'll show the two terminal names. Means as we told that first we have simulated the two terminal names in Coventry, and then this specification, actually the specification is 25 nanometer is the air gap between two electrode, and this is roughly gives 1.5 volt as a cooling voltage with a air gap of 25 nanometer. So even in Coventry, the displacement also shows it is almost means when the cooling voltage occurs. So from the bottom, so 1/3 of the air gap that gives the cooling voltage. So it is almost showing the 1.5 volt as a cooling voltage. Then we move to the fabrication. So fabrication steps is basically means we need the two means I have used the EBL, electron beam lithography. So we need two masks, two level of mask, and then we have varied the dose also. So we made the anchor as well as the suspended beam. So I mean, this is the fabrication steps. So silicon dioxide, and then on top of it is basically chrome gold made these two beam. So and then finally I have used the acetone lift off, and then means followed by the plasma ashing for this artificial layer removal to release the beam. So this is the same images. For the fabricated 2D names. So it is actuation area is basically this. There's a means two electrodes. So that is the actuation area. But the total names footprint is basically includes all the contact pads. So it is 39 means roughly 40 micrometer square. So, but the problem is that in case of names, that tiny names fabrication, we cannot see from the same images point of view that what is the air gap. So that's why we have to go for the measurement. So now if I see that the DC characterization, so it gives roughly 1.5 to 1.6 volt in case of measurement characteristic. As I show in case of commented simulation also, it gives roughly that. And it matches with the theoretical results also, theoretical calculation. So it is 1.44. So based on that, we can conclude that yes, it is well matched with the fabrication as well as the simulation and theoretical also. So this gives the electrical parameters. If you see that the add-on is basically 150 ohm per micrometer, and subsequently I have calculated the conductance also, and it is seeming also very low, so 0.35 femtofarad. So I'll show the application side also. So that is the overview of the 2T names, what we have fabricated as a preliminary devices. So yeah, so transient characterization also we have performed. So it gives the 15 nanosecond delay. So it is very low mechanical delay we have achieved as compared to the other reported works, and as well as it gives means parallelly it gives the low cooling voltage as well as the mechanical delay is also in terms of nanosecond order. So it's a good. I mean, it can be a replacement candidate of the two-terminal device in electronic applications, and it shows the good behavior of the pulse characteristics also. So this is the overview of the two-terminal names, and then we move to the three-terminal cantilever names also, and that we have published in theory recently. So this is actually means first we have performed the Coventry simulation. So it gives kindly 50 millivolt switches. So where the first one means this is the lowest pulling voltage ever reported in the paper. So, but first when we have simulated, it gives the 50 millivolt. So from that we move forward, and then we have started the fabrication. So fabrication is basically almost similar kind of means we have used the sacrificial layer by EL9 and PMMA, which is the electron register of PBL, and means the almost similar, but for this case we need 3 level of mask, because the first one is the gate and drain electrode formation, and then second one is the means the anchor formation of this beam, and then finally for the means beam, that is suspended beam formation. So there's a 3 level of mask we need. So and it is the 100 nanometer air gap, and then finally the lift off is happened through acetone solution and followed by the plasmation. So it gives nicely that from the top view we don't know what is the gap, given slight tilted also in the same. Yes, we measured something, but we cannot means assure that whether it is giving 100 nanometer gap or not. So further we have to depend on the measurement characterization. So yes, so it gives almost 50 to 60 millivolt. Then we assure that it matches with the simulation as well as the theoretical result. So it gives also 15 nanosecond delay. So that's why we concluded in that paper that yes, we have achieved the lowest VPI, and BPO also with the nominal hysteresis, as well as it gives a low mechanical delay, and the add-on and overall sorry, overall capacitance is also very low. So that is the overview of 3D names, and then I moved to the last the 40 double clamp names. So why we are looking for double clamp? Because of the reliability perspective. Because as we know, for the cantilever structure and the double clamp, if we compare that, it gives a much higher stiffness. So for some certain application point of view, we move to the double clamped structure for this 40 names. So if you see that in this case, we means we able to reduce that one mask level, because in this case what I did means for the fast level of mask in the ABL, I have I have done the two gate as well as the drain also, and then in the second level of mask I have varied the dose. So in the one level I have done the anchor as well as this dimple gap also. So in that way we have managed to do all the fabrication with two level of mask in the video. So this is the same images and the same thing. I mean, it is a tilted view, but we cannot predict that yes, these things are giving almost same air gap or not. So yes, so the is a DC and transient characterization of the fabricated 14 names. It gives the 35 nanosecond. Much it is a little bit higher than the previous two cases, but still, actually, if it gives 1.2 volt, it is also matched with the theoretical ones. So I conclude that the pooling voltage it is giving 1.2 volt with 35 nanosecond. So this paper we have published for the digital circuit application using these switches. So we have simulated some big digital circuits, means the processor kind of level using these circuits, means these switches parameters. So that is actually published in theory recently. And then I will conclude that in that way that we have fabricated various structure in case of dimensional names using control ABL process, means, and we have achieved the low air gap also. And interestingly, as compared to other published works, people have generally used for names fabrication silicon dioxide as a sacrificial layer, and followed by the dry etching or the paper press etching. However, I mean, we came up with some means L9 and PMA as a sacrificial layer. I mean, it reduces the number of level of mask also, and followed by the acetone lift off, acetone solution as a lift off. So that actually worked actually. So the last thing is that proposed model means whatever I have showed, that 2T, 3T, and 4T, that might be a very useful for in terms of low standby CMOS circuits as well as the wireless sensor nodes. So if we go one by one, suppose 2T names can be a replacement for the two-terminal device in low power electronic applications. And 3T cantilever names already we have means we are working, and we have published on a we have submitted one thing that in case of DC-DC converter, it can be a fruitful candidate to minimize the various losses like conduction loss, switching loss. If we use this switch, means the low power as a 50 millivolt NAND switch with a very low parasitic capacitance resistance, if we use this switch as a converter in the converter, it will minimize the loss. Okay. And lastly, that 40 double clamp lamps, and hence these things we have recently published that zero leakage, highly reliable double clamp lamp switch, and the pooling voltage is roughly the threshold voltage of CMOS or the MOSFET switch. It can be a means a very good promising candidate for the CMOS switch in digital circuit applications. So these are the references as we publish in this relate these works. And then acknowledgements, I would like to thank that the CEN. Yeah, it means all these means 2T, 3T, and every names fabrication was done in SAIN only. And then means I am getting the Prime Minister Fellowship, so through TST and Intel also our funding agency. So thank you so much.
Okay, so thank you, Sumit, for your talk, and
Yes.
also it looks quite an interesting work actually.
Hello. Hello.
Yeah, Sumit, just a minute.
Hello. Okay, sir. Okay, sir. Sorry, sir. Sorry, sir.
So I think something wrong with the Professor Pushparas. So this floor is now open for the questions. So if
2D,
any,
3D, and 4D. Can you hear me?
Yes, sir. Yes, sir.
Yeah, so basically, your sacrificial layer was common for 2D, 3D, and 4D, or in all of them?
Yes, sir. Yes, sir. So, yes, sir. For
Yeah.
all the
Okay.
stages, GLD and PMMA, there is sacrificial layer.
Okay, and you mentioned that you use the wet process to remove the sacrificial layer, right? So,
Yes, sir. Yes.
so did you get any problems like some like extraction problem or something while removal of this one?
Exactly, sir. Yes. So we have worked on that a lot. So the to PMMA or EL9 thing, we means we about classification also so that HMM is there. It will be removed. But it is very difficult actually. Means we have done it much more than means we have we have done new application. So that is one of the problems. And I want to tell you something that we were working on that tiny yard because people have showed many 500 nanometer each of them. So that 2500 nanometer is also difficult.
Sumit, I think there is some problem with your voice. So it's like
I
mixing up actually. So can you?
I think Sumit, Mr. Sumit, some echo is coming from your sides.
Okay. So one second.
Yeah, now it's okay. Now it's okay.
Okay, sir. Okay, sir. Okay, yeah. So that is the thing. Means it is difficult because I mean to manage that tiny air gap, and so we have faced the restriction problem a lot. But in that means, however, means in my PhD journey, means past initial years, I have not done anything. So that is the problem. Yes. Then we came up with some strategy.
Okay, so actually my question is like, because I want to know your let's say your comment, because you are using this PR as a alternate to the silicon oxide sacrificial, right?
Yes.
So
Yes, sir.
let's say if you make 10 device, how many you can really release successfully with 25 nanometer air gap?
The yield is, sir, basically 50 to 60%, roughly 50 to 60%.
And regarding the 3T switch, right? So what really motivated you to go for 50 millivolt pull-in, so low? So what is the application for going?
Yeah.
And actually, I'm surprised that because your air gap was not very small; it was around 100 nanometer here. So
Yes, sir. Yes.
how come this 50 millivolt pull-in with 100 nanometer looks very how did you get it?
So actually, sir, in case of TD also, we got the same type of comment. So actually, earlier means in the Berkeley, actually they have achieved this 50 millivolt thing, but they have used the sacrificial layer as people used the silicon dioxide as well as the vapor phase etching, all these things. But actually, I can say that frankly that I mean we don't have the vapor phase etching facility till now. So that's why I tried. I did this thing in case of acetone solution only. But yes, I mean the control that the EBL does, I have done some means of dose variation and everything in the EBL. And then the acetone solution, if you did that for the lift off, I means warm vapor, and in that way many things I have tweaked actually. And then finally I came up with the 50 millivolt switch, but it did a lot of time actually. So and we have motivation that from that simulation point of view, that simulation and theoretical value it matches. So that's why we thought that we came up with the 50 millivolt as a measurement result. So then we will be the first one. I mean, and the application perspective, we have also submitted that using these switches, what I talked that for the converter loss, Actually, if you know we know the switching losses is CV square into F. So the pooling voltage is very low. It's a very low, and as well as the parasitic capacitance is also very low. So if we compare with the traditional CMOS switches, what we put in the converter means a DC-DC converter, and so that is very much switching loss we can achieve. So that is the application even we have submitted also. So that is the application we are focusing on.
Okay, and what are the materials actually for the switches? So what is your beam made of?
Yes, sir, chrome gold only.
Oh, it's a chrome gold. Okay. Okay, so yeah, it is a nice work actually. So thank you, Sumit. I think, and also, maybe one last question. So is your context basically, degrades after a few cycles? Did you check?
So, sir, that the duty cycle is oh, so 14 names there basically it gives much more we got like a 5,000, but the current compliance is low. I showed that the 1 milliampere, if you increase the microampere level, then it gives at least this 1K5 number of reliability. Even this thing is I mean reported in this paper also. I have compared with many reported works. So means we have achieved with 1 microampere compliance at least 5K result, means 5K switching cycle. After that it degrades. So this 14 length is much more we can say that it is much reliable as compared to that 50 millivolt cantilever.
Okay, so one last question. How did you manage the stress? Because with this thin structure, there is a lot of stress actually, and you are using metal also as a switch, right? So of course there are a lot of issues with the stress, and then wet releasing. So you did not encounter any stress issue?
Stress issues are actually that beam degrades means due to Joule heating effect also, and means heat breaks actually. Whenever suppose I apply the voltage, so suddenly it gives the state means it means shorted, so it breaks. So I mean addition problem what I did for the sputtering, I did very low deposition means the pressure and so pressure is very low while depositing, and then I cool down also very low ramp rate. That is one thing. And after that means wet solution also. After the wet solution, then I means before entering into the plasma ashing, so plasma ashing also I did very controlled manner actually. So we came up with that strategy or solution a lot. I mean, and then acetone solution also I did some tweaking, but other than that I don't have that much of means strategy in my hand to tackle that addition. And means for the addition means addition perspective, I have done some simulation as well as in simulation and the theoretical result also. That actually basically I have given in the paper of 50 millivolt names paper. So actually this type of question means this type of question I got from the reviewer also. So that's it to tackle that thing. All this simulation theoretical thing I have means whatever published thing in the 50 millivolt cantilever names. I did all this thing. It is in this paper. But yeah, means fabrication perspective. That is the thing. What I did.
Okay, so Sumit, thank you. I think we will go through with your papers also, because that things should be mentioned in your paper also. So let's thank you. We are now let's thank the speaker one more time, and I would like to thank all the speakers who was here in the symposium. If anybody has any questions, then we can go. We can ask them quickly. If anyone in the participant has any question, you can ask directly. Okay, so if no questions, then thank you, Sumit, for your presentation, and good luck for your future. So okay, we are coming to the end of our session now. So thank you for the invited speakers, and also thank you for the participants for the listening. Okay, So we can take a leave now actually. Thank you.
Hello everyone. Am I audible to all? Hello? Am I audible to all?
Yes, sir.
Okay. So my name is Dheeraj and I'm going to organize this poster session for remaining students uh, who are not able to present their poster on day 1 and day 2 due to some technical or maybe some other issues, so some timing issues. So I will mention one by one the symposium name and their poster number. So they will present for 2-3 minutes for their poster, not more than that. Otherwise, time will exceed and others will not get the chance to present. All right.
Yes.
So I'm going to start one by one. The first symposia is photovoltaic and energy harvesting. So the first poster number is 137. Dr. Sushmita Mitra. Again, poster number 137, Dr. Sushmita Mitra. All right, she's not there. Next poster is 138, poster number 138, Dr. Kumar Prasenjit Pradhan. Poster number 138, Dr. Kumar Prasenjit Pradhan. Okay, he's not there. Next poster is 157, Miss Saima Cherukat.
Hello, yes, I'm available.
Yeah, you can share your poster to all and you have 2-3 minutes to complete your poster. Okay.
Yes. So can
And
I
if is
get
there
that
any
because I have
questions?
not the, but yesterday actually it was shared by the host. So currently I don't
Okay,
have it
you don't
present.
have, okay, I can share for you, no problem.
Yeah, sure. Thank you.
Yeah. Is it visible to all?
Yes.
Yeah, please, Saima, go ahead.
Okay, thank you, sir. So good evening, everyone. So we a team at NCPRE at IIT Bombay. So we are studying this chemical diffusion using different methods. So you all know that the de facto industrial method is like POCl3 source, where we will be having a bubbler and then the nitrogen will be passed through it, and then the diffusion furnace it will be getting roasted, and then we'll get the diffusion furnace. And the other one method is like screen printed diffusion. So it will be just like a normal screen printer where we have a dopant case which will be containing phosphorus particles, and then it will be screen printed on the sample, dried, and then we'll put into the furnace. So in this paper, we are comparing both the type of diffusion and screen. So as per the experiment plan, if you could see that everything is similar, the only thing is like we have it batch A and batch B. So due to the availability of the 2-inch diffusion furnace, the sample size was limited to 2-inch. That's why we had to laser cut it, but otherwise everything is similar, like all the passivation as well as the firing techniques are similar. And for the firing of screen printed and open piece, we have used a peak temperature of 850. Whereas for the POCl3, we have 845, but with a much complicated temperature profile. So the lifetime of both the batches was like around 17.24 like PDC and 23.44 POCl3. And the sheet resistance were also quite comparable, like before HVAC and after HVAC. And then we could fabricate the solar cells of comparable efficiencies of like 16.9 for PDP as well as 16.95 for POCl3. The main limitation was with respect to VOC as well as fill factor. But if you compare both having the same structure, we could say that the screen printed open phase can be a very possible form of diffusion. And other advantages will be that we can have pattern junction, which we could use for like say IBC or like bifacial solvers. Thank you, sir.
Okay, thank you, Saima. Is there any other question you can put in a chat box so that she will be answer you? Okay, so next poster is the poster number is 158.
Here's a result from the web.
Dr. Bijinder S. Sanger. Poster number 158, Dr. Brijender S. Sanger. All right. Next poster is 160, Mrs. V. Vijayalakshmi. Poster number 161, Mr. Saurabh Parekh.
Yes. I'm available.
You are here.
Sir, can you share the poster?
Sure. Is it visible to all?
No, it's not visible. Yes, now it's almost visible.
Okay, you can proceed.
Yes. Good afternoon, everyone. My presentation is entitled for studying the impact of graphitic carbon nitride quantum dots as an additive in the bulk heterojunction layer and studying its optical properties and photovoltaic performance. So in this, firstly we prepared the graphitic carbon nitride quantum dots using the chemical oxidation method, which involved in which it was treated with nitric acid for exfoliation process, and subsequently by hydrothermal treatment for the formation of quantum dots was done. And to confirm the formation of quantum dot, we performed the X-ray diffraction, and TAM results were shown as shown in the middle top portion, and the layered structure for the as that of bulk was retained in the quantum dots, suggesting that the 2D nature is retained in this, and the quantum dot size, they were ranging in the 2 to 5 nanometers, as shown in the by the histogram for the corresponding time image. And then after the preparation of these quantum dots, it was incorporated into the bulk heterojunction, that is P3ST PCBM active layer, and we studied the morphological and optical properties. From the morphological properties, it was obtained that almost 2 volume percent of the concentration of quantum dots obtained the optimum phase separation in the and better crystallization, therefore generating more efficient dissociation, and leading to separation of the charge carriers. And to confirm, and then further, from the optical properties, it was observed that the quantum dot exhibits the Fret effect. In the Fret effect, the energy was transferred from the quantum dots to the host polymer, that is P3HT, generating more number of excitons, as can be seen from the corresponding PL spectra as shown in the right hand side, that with the incorporation of the quantum dot, the emission intensity of the P3ST increased because of the energy transfer mechanism, generating more number of excitons. The same can be revealed, can be uh, obtained in the photovoltaic performance also, where we observed almost 40% improvement in the device efficiency compared to the pristine one. That is 2 volume percent, that was the optimized concentration of the quantum dots, which generated almost 3% of the power conversion efficiency, almost 40% higher than that of the pristine ones. And as the concentration increased, it again the efficiency again started deteriorating because of the reduced phase separation in the material in the active layer. They were generating less number of excitons because of the aggregation. So in this work, we can conclude that the introduction of the quantum dots improved the photovoltaic performance due to the multifunctionality, that is morphological improvement, as well as due to the Fret effect of the quantum dots. So this is all. Thank you. So it's done. Hello.
Okay. Thank you, Saurabh. Any questions? All right, let's move on to the another one. No question is there. Next question number is 163. Miss Sobia Wahid.
Yes. Hello.
Yes, Sobia.
Yes. Please put my presentation in.
Yeah, I'm going to share. Wait.
Okay.
Is it visible to all?
No. Okay.
Yeah, it's visible?
Yes.
Okay. Go ahead, Sobia.
Okay. Hi everyone. This is Subia Vaid. My work is actually focused on identifying the key limiting factors for ultrasonic spray deposition for the application of organic photovoltaics. So basically what we have done in this study is implying ultrasonic spray deposition for organic photovoltaic solar cells, and the material I used was P3HT PCBM. So the basic study that we have done is actually identifying the limiting factors that actually plays role or actually creates hurdle in achieving spin comparable spray deposited organic solar cells. So the study, we compared spin and spray as well as we also tried some attempts to improve the spray deposited film in morphology as well as in OPV performance. As you can see, this is the setup for my ultrasonic spray deposition, where ultrasonic nozzle was used and the active layer solution was fed through a control panel. So all the things were digitally controlled in temperature and all. So the results were as you can see in the results, the spin deposited film and the spray deposited film have almost equal thickness, or you can say equal absorption for all the spin and spray deposited films. However, as you can see, the shoulder, which is actually corresponding to the pi crystallization of the P3HT film, is getting enhanced when the substrate temperature in spray deposition is getting increased. That means there is a role of substrate temperature in spray deposition. The other thing that we found was, if we put substrate temperature as well as substrate vibration, we can see that not only it increases the device performance, but also it actually increases the PL quenching of our films. And the crystallization does play a role in film crystallization, as we can see from XRD studies. Okay, so the film that we have seen, organic photovoltaic device performance, as you can see, there was 85% improvement when we applied vibrations on the substrate, as you can see, and the comparable efficiency and performance was obtained in spray deposition when vibrations was applied compared to the spin coating. But however, as we can see in this IV characteristic, the fill factor is still low compared to this spin coated film, that we have to work further. And the reason for low fill factor can be easily seen through this dark IV characteristic, where the reverse saturation current is higher in case of spray deposited film. That might be because, as you can see, I cannot scroll it down. The optical images, as you can see, the optical images, it clearly show that there are some boundaries present due to the droplets, which are not actually present in spin. That might be the reason why we are getting higher reverse saturation current in case of spray deposited film. However, the efficiency was almost close, or even you can say that in spray with vibration, we got better efficiency than the spin coated device that we've obtained in our lab, and got around 3.5% efficiency for P3HT PCBM. So in conclusion, I can say that we can achieve a spin comparable device with spray deposition, as well as we can also scale the technique for large area application. All we have to do is just take some factors into account and try to optimize those things. Additionally, applying the substrate temperature and the substrate vibration will help us achieve the goal. Thank you.
Okay, thank you, Sobia. So next poster is 137, Miss Tanvi.
Yeah, hello. Am I audible to all of you?
Yeah, you're
Yeah,
audible.
so let me share my screen.
All right.
Is it visible to everybody?
Yeah, it's visible.
Okay. So good afternoon all. This is Tanvi from NCPRE IIT Bombay. So this work is actually, we are working on the investigation and probing layouts for IV measurement of silicon wafer solar cells. So basically I'll start with the basic general introduction. So as we know that reliable electrical performance measurement of commercial silicon solar cells is a concern for manufacturers, project developers, and investors. So we have lots of standards. So IEC has devised lots of standards and procedures to standardize the all the characterization process. However, still there are some gray areas which we are not able to cope up with. So in spite of following the IEC standards variation, we can see that there are variations in measurement uncertainty which are observed. So during the intercomparison of testing facilities, so that is actually a major concern for testing facilities. So probable reasons are including non-uniform illumination, spectral mismatch, shadow of probing bars, and incompatible probing schemes. So in our preliminary work and so how we get the motivation to start working on this. So we have done like some of the things like shadow created due to the fixed width of probe bars during measurement reduce the current generation along the contact bus bars. So we have observed this. So difference in, and then another observation was the difference in bus bar and probe bar bits is mainly responsible for the power loss. That was second observation. So it is not only the contact bus bar shadow, it is also the difference in the widths of both. Then another is inclusion of then we found it very viable that inclusion of shadow correction is essential. So inclusion of shadow correction in lieu of current PV industry trends of PV bus bar width reduction is highly recommended to avoid the measurement variations. That was after the observation of these two factors. Notably, shadow correction brings down the magnitude of variation in short circuit current density and open circuit voltage to the acceptable limits applicable for industrial size crystalline silicon solar cells. Nonetheless, variation in the full factor measurement did not get affected by the shadow correction, which was another observation of ours in this preliminary work, which can be taken care of with optimized probe context. So now this was the motivation. Now coming to the methodology part. So we find that even we are correcting for the shadow correction and other factors, but even then, thus probing layouts is not a standardized one. It is not a standardized in the IEC standard itself. So we have developed an methodology for it. So we have developed an analytical expression for it to find the optimal number of current pins which can be suitable to be connected to a bus bar. Potential difference across the bus bar is observed by simulating a unit solar cell in COMSOL multiphysics by varying number of current pins. Two contact probing beams schemes we have investigated just for now to prove that how our theoretical expression is working. So this we can see here. This is the analytical expression we have developed. So here n is the value which is giving the how many number of current pins which can be adopted by a testing facility to avoid this measurement uncertainty arising due to the this difference in current and voltage pins which is present in the probing layout. So we have developed this expression. So we can see here so many parameters. So we have I have given this table here. So we can see here that there are the cell parameters which we have used: cell length, number of fingers, finger spacing. So by using all that, this theoretical formula gave us the value of approximately that 20 value. So that means that 20 number of current pins, if it is the optimal expression, optimal value of the current pins which can be accommodated on the probe bar, so that we can play safe to avoid the measurement uncertainties. So here we have given the two contact probing schemes we can see lie down in just besides this table. So there is L1 strategy and L2 strategy. So I think all of us would be aware that we have this L1 strategy in which we have sense pin in the middle and other current pins are alongside it. And then we have the L2 strategy, that is another strategy into the talks of research, that is that we have IV pairs. So we have current pins, we have a voltage pin in this configuration. So we have simulated this to see that how our results are going to fit into this. So here we can see right at the right that simulations are there. So we have used the COMSOL multiphysics, and then we have visualized that variation of fill factor, variation in efficiency. Then we have have compared the single sense pin configuration and IV configuration by using and fitting our number of expression which we have arrived by you as of 20 current pins. So in these two strategies, L1 and L2, by using our theoretical expression formula, we found out when we reach, we can see that in the horizontal axis, when we reach around, when our number of current pins reaches to the 20 value, so almost our difference in efficiency and difference in fill factor becomes negligible, so which is actually lesser than 1%. So it is very well accepted in measurement uncertainty limit for any testing facility. So that's a good confirmation of our theoretical expression, which is shown by our simulation and confirmed by our simulation. Here in the down third figure, we can see that we have also compared pin wise that how it if we increase the number of current pins, how it is affecting the potential electric potential. So we can see that if we have increased the number of pins to the 20, then almost we have achieved the equipotential distribution condition. So that is actually helping us to feel the reduced resistance effect which play into picture when we don't have the optimal strategy, optimal probing layout strategy. So we want to minimize the resistance effect which is experienced by the bus bar itself. So we want our probing layout to be independent of this resistance felt by the contacting probe bar. So in the end, I would like to summarize all the things. So non-availability of contact grid standardization based on number and placement of contact pins for IV measurement generates the necessity to optimize contact probing layout, which was also the motivation of our work. So then second is contacting probe geometry can influence potential distribution along the bus bar, leading to uncertainties in current measurements and hence fill factor and efficiency. Two different probing schemes, L1 and L2, we have compared in this, and we have seen that our simulation results confirm our theoretical modeling by showing the minor difference between our proposed contacting strategy and the existing probing strategy. Studies show single voltage pin placed at the middle position with optimal number of current pins with L1 strategy is sufficient to reduce fill factor and efficiency variations to 0.05% from 0.25%. So which is actually going to be very fruitful when we are going to estimate overall measurement uncertainty. So this is very important. So I hope this study of ours is going to create a path in future for other laboratories as well. Thank you.
Thank you, Tanvi, for the wonderful presentation. But you took too much time actually. We are trying to present in 2 or 3.
Sorry
Okay.
for that. Yeah.
So
I will stop
other
sharing now.
Yeah. Thank you so much. Thank you. So next poster number is 165, Ms. Shrijit AY. Poster number 165, Ms. Shrijit AY. Okay. So no other poster from this session, photovoltaic and energy harvesting. So I move on to the another session, that is spintronics devices for memory and computing. So poster number is 191, Ms. Goodson.
Yes, sir. I'm audible.
Yeah, you are audible.
Let me share my poster.
Sure. Please make sure that the presentation should be for 2 or 3 minutes.
Yes, sir.
Okay.
Yes.
All right. Go ahead.
Yes, sir. In this poster, I have presented a novel design of fast and area-efficient hybrid MTG CMOS spintronic approximator. This hybridization stretches Moore's law beyond its limit. The main objective of our work is to show the effect of using different switching schemes, STT, SHE, VCMA, and using the different value of VCMA coefficient 33, 105, 290, and a different magnetic field 20, 22, 24 millitesla on the performance of the adder, and the superiority of the proposed approximate adder with its counterpart, exact adder. This is the vertical structure of MTJ. It comprises of three layers, free layer, and a barrier layer and a reference layer. Depending upon the orientation of magnetization of free layer and a reference layer, MTJ offers resistance. If both are in parallel, act as a low resistance. If it is in anti-parallel, act as a high resistance device. This is the circuit diagram of the adder. This is sum circuit, C out and approximate sum. I have done the approximate sum by removing two transistors from the exact sum circuit. This is a dynamic circuit work in two phase. In pre-charge phase, output nodes are pre-charges to the VDD minus VTH and saves energy. In the evaluate phase one of its output nodes are discharges to ground and pull the other node to VDD. This is the transient response of approximate adder, which validate the functionality of our proposed approximate adder. This is the result at different VCMA coefficient and H external value. By changing the VCMA coefficient and H external, sensing energy and sensing delay does not affect significantly. This is mainly the switching parameter. If we change the VCMA coefficient from 33 to 290, it affects its switching energy by 68%, and if from 33 to 105, it saves energy by 88%. And if we change the H external value, it mainly affects its switching time. If we change the switching time from 20 millitesla to 22, it basically reduces the switching time by 41%. And in case of 22 millitesla to 24, its switching time is reduced by 39%. Our proposed approximate adder are 4.37 and 1.38 times faster than the existing adder 1 and adder 2. This is all, and our proposed approximate adder are superior with existed counterpart. This is the energy and the delay, PDP and ADP by this much percentage, and we will conclude that. This is a logic in memory device. In this case, we does not need the separate memory for its storage. Approximate adder is and our proposed approximate adder is 8% more area efficient than existed adder. And by varying the VCMA coefficient and magnetic field, we can change the switching energy and the switching time. Thank you.
Thank you, Gulshan. Nice presentation. So if is there any question, you can ask from the chat box. Okay, so that's the only one presentation from the spintronic device in memory and computing. Next section is emerging logic, memories, and neuromorphic devices. Poster number 249, Mr. Agra Deep Paul. Poster number is 249, Mr. Agra Deep Paul. Okay, he's not there. So next poster is number 250, Mr. Jani Babu Singh.
Hello, yes. Am I audible?
Yeah, you are audible.
So can I share? Are you sharing?
It's up to you. If you want,
okay.
I can share.
I'm sharing.
Okay, go ahead.
Can you see me the screen?
Yeah, it's visible.
Okay. So today, my topic is designing and mathematical model of interspike interval of temporal and neuromorphic encoder for image recognition as an application. So neuromorphic encoding is where you take any signal and it converts into the conversion of into a spike trains. So here we have considered the temporal encoding scheme. So where the temporal encoding scheme is defined by the information is the input signal information is difference between the two consecutive spikes, that D1 and D2. This has been taken as a temporal encoding. So there are mainly three types of encoding schemes. using neuromorphic, that is rate encoding, time to first spike, and temporal encoding. So here we have taken the temporal encoding scheme. So we have implemented the temporal neuromorphic encoder using a cadence virtuoso tool, EDA tool. This is the block diagram of the overall temporal encoder. In the first step, where the image is given with an input voltage, this is converted by the input voltage, which is image pixel values 0 to 255 is converted into a voltage, input voltage, that is pixel by 2 as a resolution for, and then this Vin is given to the pixel to excitatory current module, and these excitatory modules are given to the neuron block. These neuron blocks we have considered for 3 neurons, and corresponding 3 interval spikes will generate. Each neuron will fire in accordance to the after reaching into the threshold value set by VTM. This will generate a spike for each neuron, the corresponding spikes, and the difference between the first neuron and the second neuron, that is D1, and second neuron to the third neuron, that is D2. And corresponding these mathematical model is also derived, and these mathematical model and the simulation model has been verified in the simulation and math in the results, and compared that only about a 2.2% error is observed. The data set we have taken to be MNIST data set, and it's approximately equal for all the data sets we have considered, the data set images considered. And finally we conclude that this temporal encoder is designed, and it can be used as a for a reservoir computing and any other applications where the images can be taken, and temporal encoding scheme can be used as an encoding scheme. Okay, and that's it.
Okay, thank you, Jani Babu.
Okay, thank you.
Any questions, please put your questions in the chat box. All right, so that's all for this emerging logic memories and neuromorphic device session. So let's move on to the another one, and that is photonics and plasmonics. And their poster number is 166, Miss Dipti. Poster number 166, Miss Dipti. All right, she's not there. So let's move on to the next poster. Poster number 168, Dr. Richa Goel. Poster number 168, Dr. Richa Goel. All right, next poster is 171, Mr. Saurabh Pan. Poster number 171, Mr. Saurabh Pan. Okay, so nobody is there. So, but I have seen some names in my participant list. So I will call those posters number again, which are not participant earlier. So please check if someone is there. Please, you can share your screen and present. So I'll call one by one. Poster number 138, Dr. Kumar Prasanjit Pradhan. Poster number 158, Dr. Brijinder Singh Sangar.
Hello. Sir, yes,
Yeah.
I am available.
Ria, yeah.
Yes, sir. Ria
Please,
Katyar.
yeah. You can share your screen or I can share for you.
So you can share for me.
All right.
Mhm.
Is it visible to all?
So, yes, sir, it is visible to me.
Okay, so please go ahead.
Okay, thank you, sir. Okay, a very good afternoon, everyone. Today, I, Ria Katyar, and I'm here to present the poster titled Numerical Simulation of High Efficient Perovskite Solar Cell Based on SCAPS. In this work, the planar heterojunction based perovskite solar cells have been simulated with the program SCAPS. The structure of the simulated device is the N-type TiO2, intrinsic CH3NH-Tb3, and P-type is pyro-omitted. For making our model more practical, we have inserted an interface layer between the junctions. The thickness of the absorber layer plays a very crucial role for the device optimization. We have also analyzed the effects of the different defects in the bulk and at the interface of the perovskite layer. The simulation results indicate that owing to the low defect density combined with the superior absorption coefficient, the perovskite solar cells can exhibit both the high open circuit voltage and a very high value of the short circuit current. We have found that the type and the thickness of the absorber layers again plays a very important part in the functioning of the perovskite solar cells and shows the direct effect on the values of the short circuit current, the fill factor, and the open circuit voltage. It can be concluded from the simulation study that the 1000 nanometer thin perovskite solar cells, sir, so the poster is not visible.
Sorry.
Mhm.
Go ahead.
Okay. So it can be concluded from the simulation study that the 1000 nanometer thin perovskite layer can be used for the photovoltaic device applications with less defect density and bulk interface as well. Thank you, sir.
Thank you, Ria. Is there any question? All right, let's move on to the other one. Poster number 160, Mrs. V. Vijayalakshmi. Okay. Next poster number is 165, Ms. Shirijit AY. All right. Next poster number is 249, Mr. Agyadeep Paul. Okay. Next poster is 166, Ms. Deepthi. Next is 168, Dr. Richa Goyal. Okay. Next poster number is 171, Mr. Saurabh Pan. Okay, no one is there. So Preeti, are you listening? Preeti Kumari.
Yes, sir.
So Preeti, you can share your poster and present your work. Preeti, are you listening?
Yes, sir.
Yes, you can share your poster. Okay, Preeti, I am sharing on behalf of you.
Sir, एक second.
No problem, I'm sharing.
Sir.
You just present.
Sir, visible.
Wait.
Sir, visible.
Yeah, is it visible to all?
Yes, it is visible.
Yeah, please go ahead, Preeti.
My topic is ESCAP's modeling of solar cell deployed a back surface field SNS layer for performance upgradation. This topic abstract for this purpose improve efficiency of solar cell. This is used in CZTAAC based thin film photovoltaic cells are suitable candidature for PV cells. Since CZTAAC used as absorber layers has easily turnable band gap is non-toxic and economical. Using back surface field is one of the primary method of upgrading the efficiency of PV cells. The BSF layer reduces the wastage of photo-generated electrons at the back recombination sink and hence improve efficiency of the cells. My work, we have analyzed the performance of absorber layer based photovoltaic cell with SNS as VSF layer using ESCAP software simulation. Diagram shows without SNS and with SNS layer. Then simulations results are given in the table. Then conclusion, we believe our work could play a crucial role in renewable energy of solar cell, play a vital role in the improve efficiency and economically with the natures. After simulations, results are given with increase in band gap from 1.0 to 4 nanometer band gap, increase efficiency, short circuit current, open circuit voltage, and fill factor. Then after it is saturated. Sir, characteristics given in the graph. Thanks.
So that's all from your side, Preeti?
Yes, sir.
Yeah, thank you so much for the presenting this poster. Any questions from the participant? All right, so that's all for this session. And I would say thank you to all for participating in this session. Now I'm concluding this session and wind up this. So thank you all. Thank you so much.
Thank you. Thank you, sir.
Thank you.